stand in front of a mirror. Go ahead, really look at yourself. Run your hand down your arm. Notice the texture, the smoothness, maybe a few fine hairs catching the light, but nothing you'd call fur. Now imagine standing next to a chimpanzee doing the same thing. Your closest living relative, separated from you by only about 6 million years of evolution, staring at its reflection through eyes remarkably similar to yours. Except the chimpanzee is covered, absolutely covered in thick, coarse hair from its scalp down to its toes. Dark fur protecting every inch of skin except its face, palms, and the soles of its feet. You look like someone took that chimpanzee and shaved it. Not partially, not leaving some fashionable pattern. Shaved it completely, obsessively, leaving only scattered patches where hair still grows thick. Your head, obviously. Your armpits and groin, sure. And depending on your ancestry and genetics, maybe some facial hair, some chest hair, perhaps a dusting across your forearms. But compared to the chimpanzee, compared to gorillas and orangutans and bonobos, compared to every other primate on this planet, you are essentially naked. Strange, isn't it? When you really stop to think about it, when you really look at yourself compared to your evolutionary cousins, humans are bizarre. We're the weird ones, the outliers, the naked apes walking around pretending this is normal. If you're here to fall asleep, perfect. That's exactly why I make these videos. The sound of my voice, the slow unraveling of deep mysteries, the kind of questions that sit in the back of your mind during quiet moments. So maybe hit that subscribe button and tell me in the comments where you are right now. Tokyo at sunrise, Mumbai at midnight, somewhere in rural Montana at 3 in the morning. It's fascinating how we're all here together, wondering about the same vanished fur coat our ancestors shed millions of years ago. Here's what makes human hairlessness so strange. It's not just that we lack fur. Lots of mammals have reduced hair coverage, but almost all of them have very specific reasons for it, reasons that make immediate, obvious sense. Whales and dolphins lost their fur because hair doesn't work underwater. It creates drag, loses insulation when wet, serves no purpose for a fully aquatic mammal. Elephants and rhinoceroses shed most of their hair because they're massive. When you weigh 5 tons, your body generates so much internal heat that fur becomes a liability in tropical environments. Your surface area to volume ratio means you need to dump heat, not trap it. Naked mole rats live underground in stable temperature burrows where fur serves no thermoregulatory purpose, and their naked skin actually helps them navigate tight tunnels. But humans? We don't live in water. We're not 5-ton behemoths generating massive amounts of heat just by existing. We don't spend our lives in temperature-stable burrows. We live on land, in environments that range from freezing to scorching, in conditions where you'd think fur would be incredibly useful, and yet somewhere along our evolutionary journey, we lost it. Almost all of it. We became the naked apes. And here's the thing that should really bother you. We're not just hairless compared to other apes. We're hairless compared to almost everything. Out of roughly 5,000 mammal species on Earth, only a handful are effectively hairless. That's less than 1%. Humans are in a vanishingly rare category, sharing our nakedness with whales, elephants, hippos, rhinos, walruses, and naked mole rats. Every single one of those other species has an obvious environmental explanation for their hair loss. We don't. At least not an obvious one. Look at any other terrestrial mammal our size. Wolves, jaguars, deer, chimpanzees, all of them covered in protective fur. That fur serves so many functions it's almost hard to list them all. Insulation in cold weather, keeping you warm through frigid nights, protection from direct sunlight, preventing sunburn and blocking harmful ultraviolet radiation, a barrier against thorns, sharp grasses, insect bites, abrasions from rough terrain, a canvas for camouflage patterns that help with hunting or hiding from predators, a display surface for social signaling, showing dominance, maturity, health status, and critically, a home for your skin microbiome and a first line of defense against many parasites. So why did we lose all that? What possible evolutionary advantage could there be to walking around naked in a world full of dangers? This question has obsessed scientists for over a century. Charles Darwin himself was puzzled by human hairlessness. He could explain why giraffes have long necks through natural selection for reaching high branches. He could explain why birds have different beak shapes adapted to different food sources, but human hairlessness stumped him. His best guess was sexual selection, the idea that our ancestors simply found hairless partners more attractive. But even Darwin wasn't entirely convinced by his own explanation. Since Darwin, researchers have proposed at least a dozen different theories. Maybe we lost our fur because we started running long distances under the hot African sun and needed better cooling. Perhaps we spent time in and around water, like semi-aquatic mammals. Some think it was about parasites, that getting rid of fur meant getting rid of disease-carrying ticks and lice. Others argue it was about social signalling, that hairless skin allowed us to read each other's emotions more clearly. There are theories involving brain cooling, theories about sexual attraction, theories connecting it to bipedalism and upright walking. And here's the frustrating, fascinating truth. They might all be partially right. Evolution doesn't usually happen for just one reason. It's messier than that. Multiple pressures often work together, each one nudging a species towards certain adaptations. But the fact that scientists still debate this question, still publish competing papers about why humans are hairless, tells you something important. We don't actually know for certain. We have educated guesses, strong hypotheses backed by evidence, but no definitive answer. The mystery of our missing fur remains one of the most intriguing unsolved questions in human evolution. Let me show you just how recently science has been actively avoiding this question. Throughout most of the 20th century, respectable anthropologists simply didn't talk much about human hairlessness. It was considered a minor detail, maybe even a slightly embarrassing topic. Why the embarrassment? Because hairlessness is associated with nakedness, and nakedness was culturally awkward to discuss in academic settings, but also because the question seemed superficial. Scientists were focused on what they considered the important aspects of human evolution. Bipedalism, the ability to walk upright, that seemed crucial. Brain expansion, the dramatic increase in cranial capacity that led to human intelligence, obviously important. Tool use, language development, social complexity, these were the serious topics. Hair, that was just cosmetic. A side effect of something else more important. Not worth dedicating research careers to understanding. Except it wasn't cosmetic at all. As scientists eventually realized, human hairlessness connects to almost every other major feature of human evolution. It's intimately linked to how we regulate body temperature, which affects where we can live and how active we can be. It's connected to our unique sweating system, which enabled endurance activities no other primate can match. It forced changes in skin pigmentation that led to the diversity of human skin colors we see today. It created vulnerabilities that drove us to invent clothing, master fire, and build shelters, essentially jump-starting human technology and culture. The loss of our fur wasn't a minor side note. It was a transformative event that rippled through every aspect of what it means to be human. And we're only now, in the 21st century, really beginning to understand just how transformative it was. Look at your skin again. Really look at it this time with fresh eyes. You still have hair, of course. Around 5 million hair follicles scattered across your body, actually. That's roughly the same number as a chimpanzee. Same number of follicles, radically different results. Because most of your hair follicles don't produce the thick, dark, protective terminal hairs that cover other primates. Instead, they produce vellus hairs, the fine, nearly invisible peach fuzz that covers most of your body. These hairs are so thin, so short, so light-coloured that from any distance you appear completely hairless. It's not that we lost our hair follicles. We still have all the biological machinery for growing thick, protective fur. The genes are right there in your DNA, passed down from ancestors, who were fully furred. What changed was the regulation of those genes. Somewhere in our evolutionary history, genetic mutations altered how those hair follicles function, switching them from producing visible protective hairs to producing nearly invisible vellus hairs. The machinery is intact. It's just been turned down to the lowest possible setting. We know this because occasionally the system malfunctions. There's a rare genetic condition called hypertrichosis, sometimes sensationalized as werewolf syndrome, where individuals are born with excessive hair growth all over their bodies. Not just a lot of body hair, but thick, dark, fur-like coverage that would look perfectly normal on a chimpanzee, but is shocking on a human. These individuals haven't gained new genes. They haven't mutated into something non-human. They've simply had the normal human hair suppression system fail, allowing the ancestral hair growth program to run at full strength. It's like someone removed the dimmer switch on a light that's normally kept very low. The bulb was always capable of shining bright. It just wasn't being allowed to. Cases of hypertrichosis reveal something profound. We carry within us right now all the genetic instructions for growing thick body fur. It's still there, written in our DNA, preserved across millions of years. We just evolved additional control mechanisms to suppress it. This tells us that hair loss in humans wasn't about losing genetic information. It was about gaining new genetic switches that kept the old hair-making machinery turned off. And those switches, we're finally starting to identify them. In the last 2 decades, geneticists have begun pinpointing the exact mutations that made humans hairless. There's a gene called HR, which stands for hairless, that regulates the cycling of hair follicles between growth and rest phases. Humans have specific mutations in this gene that reduce its activity across most of the body. There's another gene, FGF5, that controls how long hair grows before the follicle enters a resting phase. Humans have modified versions that work normally on our scalps, allowing head hair to grow very long, but are suppressed in other body regions. There's EDA, a gene affecting hair follicle density and thickness, with variants that differ between human populations. These aren't ancient, mysterious changes lost in deep time. We can actually date some of these mutations using molecular clock analysis, looking at how much the genes have diverged between human populations and comparing that to mutation rates. The evidence suggests the major hair-suppressing mutations became widespread somewhere between 1 and 2 million years ago. That's remarkably recent in evolutionary terms. Dinosaurs went extinct 66 million years ago. Life has existed on Earth for over 3 billion years, but humans only lost their fur in the last 1 or 2 years, barely a moment ago on the geological timescale. Think about what this means. For most of primate history, for tens of millions of years, our lineage was furred, thick protective coats covering every inch of skin. The earliest primates that evolved after the dinosaurs went extinct, they had fur. The first apes that split off from other primates 20 million years ago, they had fur. Our ancestors that came down from the trees and started walking upright 5 to 7 million years ago, they had fur. Even the earliest members of our genus, Homo, were probably still mostly furred or only beginning to lose body hair. But then something changed. Some combination of environmental pressures, survival challenges, and evolutionary opportunities created a situation where having less hair became advantageous. Individuals born with mutations that reduced hair coverage survived better, reproduced more successfully, and passed those mutations to their offspring. Generation after generation, the selective pressure continued. Hair got thinner, sparser, less visible, until by a few 100,000 years ago, humans looked essentially like we do today, mostly naked, with just a few patches of thick hair remaining. That transformation, that shedding of our ancestral fur coat, that's what we're here to explore. Not just the how, but the why. What was happening in our ancestors' environment that made hairlessness advantageous? What problems did nakedness solve? And just as importantly, what new problems did it create? And how did our ancestors solve them? Because losing your fur in a dangerous world is a risky strategy, you better have a good reason and a plan for dealing with the consequences. Over the next few chapters, we're going to investigate every major theory for why humans lost their fur. The savanna hypothesis, the idea that we needed better cooling for running under the hot African sun. The aquatic influences, the possibility that time spent in and around water played a role. The parasite problem, the deadly burden of ticks and lice that might have driven us to shed their habitat. The social signaling advantages of naked, expressive skin. The genetic mutations that made it all possible, and when they actually occurred. But more than that, we're going to trace the consequences. Because losing our fur didn't just change what we looked like, it changed what we were capable of becoming. It forced us to invent clothing, control fire, build shelter. It drove changes in skin pigmentation. It enabled a sweating system that made us the best endurance athletes in the animal kingdom. It created the possibility for facial expressions and emotional communication that no furred animal could match. It set off a cascade of adaptations that, taken together, made us human in ways that go far beyond just being hairless. Your smooth arm, the naked skin you take for granted, it's not just an absence of fur. It's a story written in genes and natural selection and environmental pressure. It's a tale of ancestors facing challenges that seemed insurmountable and finding solutions that seemed impossible. It's evidence of evolution's creativity, its ability to take what appears to be a vulnerability and transform it into an advantage so profound that it enabled one species of formerly furred ape to eventually dominate an entire planet, So close your eyes if you're trying to sleep, get comfortable, and let's trace this story back through time. Let's figure out why we're naked apes, and why that nakedness, paradoxically, might have saved humanity. Here's something that should unsettle you. Right now, at this very moment, your DNA contains complete, detailed instructions for growing thick body fur. Not the thin peach fuzz covering most of your skin. Real fur. The kind that would keep you warm on a freezing night. The kind that would protect you from thorns and insects. The kind that would make you look like every other primate on Earth. Those instructions are sitting in your genome, perfectly preserved, passed down through millions of years of evolution. They're just not being read. Think of your DNA as a vast library, thousands upon thousands of instruction manuals for building and maintaining a human body. Most of those manuals are actively being used. Your cells are constantly reading them, following their directions, making the proteins and structures that keep you alive. But scattered throughout this library are some very old manuals that almost never get opened anymore. Instructions that were critical for your ancient ancestors, but have become obsolete for you. And among those dusty, rarely consulted texts sit the complete specifications for growing primate fur. We know they're there because occasionally, very rarely, something goes wrong with the system that keeps them closed. A genetic mutation, a developmental error, some malfunction in the regulatory machinery that normally suppresses these ancient instructions. And when that happens, a human is born who looks the way all humans looked millions of years ago, completely covered in thick, dark hair from head to toe. The medical term is hypertrichosis, though it's been called many things throughout history. Werewolf syndrome, because affected individuals reminded people of folkloric creatures caught between human and animal. Ambrose syndrome, named after a particularly famous case. But the most accurate description might simply be evolutionary throwback, because people with hypertrichosis haven't gained something abnormal. They've lost the modern human ability to suppress something very, very old. Consider the case of Supatra Sasafan from Thailand, once recognized as the world's hairiest girl. From birth, thick dark hair covered her face, her arms, her back, everywhere except her palms and the soles of her feet. Exactly the pattern you'd see on a chimpanzee or gorilla. She didn't have a disease in the traditional sense. Her hair follicles weren't damaged or malfunctioning. They were working perfectly, doing exactly what hair follicles in primates are supposed to do. The problem, if you can call it that, was that the normal human mechanism for keeping those follicles in check, for limiting their output to nearly invisible vellus hairs, that mechanism wasn't functioning. Or look at the historical cases documented throughout centuries before modern genetics could explain them. Petrus Gonsalves, born in the Canary Islands in the 1600s, covered head to toe in thick hair. He was taken to the French court and displayed as a curiosity, a wild man, though he was educated, articulate, and thoroughly human in every way except appearance. Several of his children inherited the same condition. Or Julia Pastrana from Mexico in the 1800s, exhibited in circuses across Europe and America, called the ugliest woman in the world by cruel showmen, though photographs reveal a woman whose only real difference from other humans was the dense fur covering her body and face. These weren't isolated mutations creating something new, they were the unmasking of something ancient. The ancestral primate blueprint, still preserved in the human genome, suddenly allowed to express itself again. It's like finding an old program on your computer that still runs perfectly, even though it hasn't been used in years. The code never went away, it just stopped being executed. Modern genetic research has identified several different mutations that can cause hypertrichosis, and studying them has revealed exactly how humans normally suppress fur growth. Remember that gene we mentioned earlier, the one simply called HR? In people with certain forms of hypertrichosis, this gene is either mutated or deleted entirely. Without functional HR, the normal regulation of hair follicle cycling breaks down. Follicles that should produce tiny thin vellus hairs instead produce thick terminal hairs. The whole system reverts to the ancestral default setting. But here's what's really fascinating. When scientists sequence the genomes of people with hypertrichosis, they find that almost all of their other genes are completely normal. The genes for hair keratin production, the structural genes for building hair follicles, the genes controlling hair color and texture, all of those are standard human versions. What's different is just the regulatory system, the genetic switches that control how strongly those hair-making genes get expressed. Remove the suppression, and suddenly a human grows fur. This tells us something profound about how humans evolved hairlessness. We didn't lose the genes for making fur. We couldn't have, really, because fur is made of the same basic proteins, keratins, that form our fingernails, our skin's outer layer, even the thin hair we do still have. You can't just delete those genes without causing catastrophic problems. Instead, evolution added new layers of control, new regulatory mechanisms that turn down the output of an ancient system that still exists, still functions, but is now kept on a very low setting. Think about what this means for understanding human evolution. Our hairlessness isn't the result of losing information. It's the result of gaining new information, new genetic instructions that say, suppress this, reduce that, limit expression here. Evolution built our nakedness on top of our ancestors' furry foundation, using the original genetic architecture but adding sophisticated control systems to modify the output. And we can actually see this process playing out in the specific genes involved. Take the WNT signaling pathway, a complex cascade of molecular signals that controls all sorts of developmental processes, including hair follicle formation. In mice and other furred mammals, this pathway runs at full strength during skin development, creating dense arrays of hair follicles that produce thick protective fur throughout the animal's life. In humans, we have an inhibitor protein called DICCOP2, or DKK2, that blocks the WNT pathway in most areas of skin. Researchers discovered this by studying mice. Normal mice have hairless foot pads, just like human palms and soles are hairless. When scientists looked at what makes those foot pads different from the rest of the mouse's skin, they found high levels of DK2. Then they created mutant mice that couldn't produce DK2. Those mice grew hair on their foot pads. The inhibitor was the key. Remove it, and the ancestral hair growth program runs unchecked. Humans have high levels of DKK2 across most of our body surface. That's why most of our skin produces only thin vellus hairs instead of thick terminal hairs. But we don't have high DKK2 everywhere. Our scalps have low levels, which is why head hair grows thick and long. The skin in our armpits and groin has low levels, which is why we retain coarse hair there. Our eyebrows and eyelashes, same thing. The pattern of where humans have thick hair versus thin hair maps almost perfectly to where we have low versus high levels of hair growth inhibitors like DKK2. This isn't speculation or guesswork. Scientists have actually measured this, analysed the gene expression patterns in different regions of human skin, compared them to the patterns in other primates. The data is clear. Humans evolved hairlessness not by breaking the fur-making machinery, but by deploying inhibitors to shut it down in specific locations while leaving it active in others. And here's the really clever part. By using inhibitors rather than deleting genes, evolution left humans with flexibility. If environmental conditions changed, if humans moved into climates where more body hair would be advantageous, the necessary genetic machinery could potentially be reactivated. We see hints of this in the variation between human populations. People of East Asian descent tend to have less body hair than people of Mediterranean or Middle Eastern ancestry. That's not because they've lost more hair-making genes, it's because they have slightly different variants of the regulatory genes, producing different levels of hair growth suppression. Some researchers think this variation emerged relatively recently, within the last 30 or 40,000 years, as human populations adapted to different climates after spreading across the globe. Colder climates might have favoured individuals with slightly more body hair for extra insulation. Hotter climates, especially humid tropics where sweating is critical for cooling, might have favoured even more complete hairlessness. The genetic flexibility inherent in using regulatory switches rather than deleting core genes allowed rapid adaptation. But we're getting ahead of ourselves. Before we can understand why different human populations ended up with different amounts of body hair, we need to understand why humans lost most of their body hair in the first place. And to do that, we need to trace this process backward through time, figuring out when these hair-suppressing mutations first appeared and spread through our ancestral populations. The timeline is actually becoming surprisingly clear. Using molecular clock analysis, a technique that estimates when genetic changes occurred by measuring how much human genes have diverged from those of other primates, and factoring in known mutation rates, scientists have dated several key events in human hair loss. The MC1R gene, which controls skin pigmentation and is intimately connected to our story, shows evidence of strong selection beginning around 1.2 million years ago. This timing is significant because dark skin pigmentation would have become critically important right around the time humans were losing the UV protection that fur provides. Other hair-related genes tell similar stories. The major mutations in HR, the gene we've been discussing, appear to have become widespread between 1 and 2 million years ago, right around the time Homo erectus was emerging as a distinct species. This was a crucial period in human evolution. Our ancestors were developing longer legs optimized for walking and running long distances. Their brains were getting larger, requiring more calories and generating more metabolic heat. They were spreading out of forests into more open environments, and apparently they were losing their fur. But the genetic evidence also reveals something unexpected. Human hairlessness didn't happen all at once. It wasn't a single mutation that suddenly made someone completely hairless, which then spread through the population. Instead, it was a gradual accumulation of mutations, each one reducing hair coverage a little bit more, each one spreading through ancestral populations, because it provided some slight survival or reproductive advantage. We can see this mosaic pattern in our genes. Some hair-related mutations are present in all modern humans, suggesting they spread through our entire species very early, probably before modern Homo sapiens even emerged. Other mutations are found only in certain populations, indicating they spread more recently after humans had already dispersed across different regions. The process of losing our fur was more like a sculpture being gradually refined than a switch being suddenly flipped. And interestingly, the process might not be completely finished. Some geneticists argue that humans are still evolving toward even more reduced body hair. In modern industrialized societies, where clothing and climate control eliminate any survival benefit to body, hair, there's no selection pressure maintaining it. Random mutations that further reduce hair growth aren't being selected against. Over tens of thousands of years, this might lead to even more hairless populations, though it's impossible to predict exactly how future human evolution will unfold. What we can say with confidence is this: the genetic instructions for growing fur are still inside you, written in your DNA, preserved across millions of years. You are, in a very real sense, a furry animal with most of the fur switched off. Your naked skin isn't the absence of something, it's the active suppression of something that wants to grow. Every hair follicle on your body is capable of producing thick, protective terminal hairs. Almost all of them are simply being biochemically prevented from doing so. This means human hairlessness is reversible, at least in theory. If you could somehow disable all the inhibitor systems, block DKL-SYN2 and other suppressor proteins, you'd probably start growing fur. Not immediately, but over time, as your hair follicles cycled through their growth phases without the normal suppression signals, you'd become progressively hairier. The genetic machinery is all there, ready to function, held in check only by molecular inhibitors that your cells constantly produce. Of course, no one is suggesting we should try this. The inhibitor systems aren't just controlling hair growth, they're integrated into complex developmental and regulatory networks that control many aspects of skin biology. Tampering with them would likely have unpredictable and potentially harmful effects. But the theoretical possibility reveals the truth about human hairlessness. We're not naked because we lost something. We're naked because we gained the ability to suppress something. And that something, that ancient mammalian fur coat, is still encoded in our genomes, waiting silently in case it's ever needed again. The question is, why did our ancestors need to suppress it in the first place? What was happening in their environment, in their lives, that made having less fur advantageous? What problems does thick body hair create that would be serious enough to drive evolution toward nakedness? That's where we need to go next, into the heat, the brutal, unforgiving heat of the African savanna, where our ancestors faced a choice between staying furry and staying alive. Imagine you're wearing a thick winter coat, not a light jacket, a serious coat with insulation, the kind designed for sub-zero temperatures. Now imagine you're wearing that coat in the middle of summer and you need to jog. Not sprint for a few seconds, but jog steadily for an hour. What happens? You overheat, dramatically, dangerously. Your body temperature rises, your heart pounds trying to pump blood to your skin for cooling. Sweat soaks the inside of the coat but can't evaporate effectively, and within maybe 15 or 20 minutes you're in serious trouble. Heat exhaustion sets in. Your muscles stop working efficiently. Your brain starts to malfunction. Push it much further, and you're looking at heat stroke, organ failure, death. This isn't a hypothetical. This is basic mammalian thermophysiology. And it's the fundamental problem our ancestors faced when they started spending more time in open, sunny environments, while still covered in primate fur. Here's what you need to understand about mammalian heat production. Your body is a furnace. Every single chemical reaction in your cells, every muscle contraction, every nerve impulse, every bit of digestion, it all generates heat as a byproduct. When you're resting, sitting still, doing nothing particularly strenuous, you're producing somewhere between 70 and 100 watts of thermal energy. About the same as an old-fashioned incandescent light bulb. That's your basal metabolic rate converted to heat. Your body has to dispose of that heat continuously, just to maintain a stable internal temperature. Now start moving. Walking at a moderate pace roughly quadruples your heat production. You're now generating 300 to 400 watts. Jogging bumps it up even further, 500, 600 watts or more depending on your speed and body size. That's like having 6 100-watt light bulbs burning inside your body. All that thermal energy has to go somewhere. It has to be dumped into the environment, or your core temperature rises, and unlike reptiles that can tolerate wide swings in body temperature, mammals are obligate homeotherms. We have to maintain our core temperature within a very narrow range, roughly 97 to 99 degrees Fahrenheit for humans, or our proteins start to denature, our cellular machinery breaks down and we die. For most mammals, the primary strategy for dumping excess heat is behavioral. Don't exercise during the hottest parts of the day. Rest in shade. Limit activity to dawn and dusk when temperatures are cooler. Watch any documentary about African wildlife and you'll see this pattern. Lions sleeping under acacia trees during midday heat, only hunting during cooler evening hours. Zebras and wildebeest grazing in early morning, then standing motionless in what shade they can find once the sun climbs high. Even animals that seem tough and heat-adapted, like elephants, spend the hottest hours largely inactive, using their ears as radiators and spraying themselves with water when available. This behavioral thermoregulation works fine if you can afford to be inactive during hot periods, but what if you can't? What if your survival strategy requires you to be active precisely when other animals are resting? What if you need to walk long distances to find food, track prey animals across open terrain, forage in areas with minimal shade? Then you've got a problem, a potentially fatal problem. This is the situation our ancestors found themselves in somewhere between 2 and 3 million years ago. Possibly earlier. The climate was changing. Africa was drying out. Dense forests were fragmenting, giving way to woodlands, then to open grasslands, the savannas that would become the crucible of human evolution. Our ancestors, descended from tree-dwelling apes adapted to forest canopies, were spending more and more time on the ground in these open environments, walking upright on 2 legs, which freed their hands but exposed more of their body surface to direct overhead sunlight, searching for food sources that were now spread out rather than concentrated in fruit-bearing trees, and crucially, beginning to incorporate more meat into their diets, which meant either scavenging from predator kills or hunting their own prey. All of this required being active during daylight hours, not just walking a little bit, but covering serious distances. Studies of modern hunter-gatherers suggest that our ancestors might have been walking 6 to 9 miles per day on average, sometimes much more when tracking game or moving between seasonal food sources. That's hours of sustained activity, generating massive amounts of metabolic heat under a tropical sun that could push air temperatures well above 100 degrees Fahrenheit. And they were trying to do all this while covered in ape fur, thick, insulating, heat-trapping fur. Do you see the problem? This is a recipe for hypothermia, for death by overheating. The math simply doesn't work. A fur-covered primate, even one walking upright, cannot sustain hours of activity under the African sun without catastrophically overheating. Let me show you exactly why, with some specific numbers. When a chimpanzee walks at a moderate pace, its metabolic rate increases about 4-fold, just like in humans. That chimp is now producing around 300 to 400 watts of heat that needs to be dissipated. But fur creates a boundary layer of trapped air next to the skin. This is exactly what makes fur such good insulation in cold weather. That trapped air is warmed by skin temperature and can't circulate effectively, creating a buffer that prevents heat from escaping. In cold environments, perfect. In hot environments while exercising, deadly. Researchers have actually measured this effect. Studies using thermal models and live animal measurements show that a fur-covered mammal exercising in hot conditions has to work much harder to dump heat than a hairless one. The fur doesn't just slow heat loss through radiation and convection, It also dramatically reduces the effectiveness of evaporative cooling, which in hot environments is the only mechanism that actually works. Here's why. There are 4 main ways mammals can dump heat. Radiation, simply emitting infrared thermal energy into the environment, works well when the environment is cooler than body temperature, but not when you're in 100-degree heat. Conduction, transferring heat through direct contact with cooler objects, requires you to be lying on something cool, not walking across sun-baked ground. Convection, using air movement to carry heat away, works decently on bare skin but poorly through fur. And finally, evaporation, using the phase change of water from liquid to vapor to carry away massive amounts of thermal energy. This is the only mechanism that works when air temperature approaches or exceeds body temperature. Humans cool primarily through evaporation. We sweat a lot. Across our entire body surface, we have between 2 and 4 million eccrine sweat glands capable of producing 1 to 2 liters of sweat per hour during intense activity. When that sweat evaporates from bare skin, each gram of water carries away about 580 calories of heat. It's an incredibly efficient cooling system. But, and this is crucial, it only works on bare skin. Put fur over sweat glands and everything breaks down. The sweat gets trapped in the fur layer, it saturates the hair shafts, creating a humid microclimate next to the skin. Evaporation still happens, but much more slowly, and the cooling effect doesn't reach the skin efficiently. Meanwhile, that wet fur becomes a thermal insulator that's even worse than dry fur, trapping both heat and humidity against the body. You end up soaked, overheated, and in serious danger of heat stroke. Other mammals that rely on fur for protection deal with this problem by panting. Dogs, cats, wolves, most carnivores, they don't have eccrine sweat glands covering their body. Instead, they have apocrine sweat glands that produce oily, smelly secretions useful for scent communication but useless for cooling. When these animals overheat, they pant. Rapid, shallow breathing across moist surfaces in the mouth and nasal passages, using evaporation there to cool blood before it reaches the brain. It works, sort of, but it's far less efficient than whole body sweating. And critically, you can't pant and run at the same time. You need to stop, stand still, and pant to cool down. Watch a dog on a hot day after playing fetch for a few minutes. It stops, sits, tongue out, panting heavily, unable to do anything else until its core temperature drops. This is fine for an animal that hunts in short sprints. Chase prey for 30 seconds, either catch it or give up, then rest and cool down. But it doesn't work for sustained activity. You can't pant your way through a 6-mile walk in the heat. You'd have to stop every few hundred yards, wait to cool down, then continue. Any survival strategy requiring sustained daytime activity is simply incompatible with fur and panting-based cooling. This is the trap our ancestors were in. They needed to be active during the day in open environments. They needed to walk long distances. They needed to track and hunt prey. They needed to forage over wide areas. But their inherited primate fur made all of this impossible without constantly stopping to cool down, which meant taking much longer to get anywhere, which meant less food gathered, which meant lower survival rates. Natural selection doesn't tolerate inefficiency like this. When there's strong pressure for a particular capability, in this case sustained daytime activity in hot environments, evolution finds solutions. And the solution that emerged in the human lineage was radical. Lose the fur, develop dense networks of eccrine sweat glands across the entire body. Create a cooling system so efficient that sustained activity in midday heat becomes not just possible, but advantageous. Research published in 2022 actually modeled this. Scientists used heat transfer equations and physiological data to simulate how well different levels of hair coverage would permit sustained activity at various temperatures and humidity levels. The results were stark. A fully fur-covered hominin exercising in typical African savanna conditions during midday would reach dangerous core temperatures within 30 to 40 minutes. Reduce the fur coverage to modern human levels, add human eccrine sweat gland density, and suddenly sustained activity of several hours becomes feasible. The model also showed something interesting about bipedalism. Walking upright reduces solar heat load by about 60% compared to walking on all fours, simply because you're presenting much less surface area to overhead sun. A quadrupedal mammal has its entire back exposed to direct sunlight. A bipedal one only has the top of its head and shoulders exposed. This reduction in radiant heat gain is substantial. But even with bipedalism's advantage, fur remained a critical problem. You needed both adaptations, upright walking and hairlessness, to make sustained daytime activity possible. Think about what this means. Bipedalism probably evolved first. Our ancestors were walking upright by at least 4 million years ago, maybe earlier. We know this from fossil footprints and skeletal evidence. But they were probably still mostly furred at that point, or only beginning to lose body hair. This would have created an awkward intermediate period. They had the skeletal adaptations for efficient walking and running. They had the body proportions that reduce solar heat load, but they still overheated relatively easily, limiting their activity during hot periods. Then hair loss mutations began spreading through populations. Individuals born with slightly less fur could be active slightly, longer before overheating. They could walk farther, forage more efficiently, track prey more successfully. They survived better, had more offspring. Those offspring inherited the hairlessness genes. Over thousands of generations, the population became progressively less hairy until something like modern human hairlessness emerged. And as hairlessness spread, another adaptation became critical: eccrine sweat glands. We don't just have a few scattered across our bodies like other apes do. We have millions, covering almost every square inch of skin. These glands had to proliferate to take advantage of the newly bare skin. There's actually evidence that eccrine gland density and hair follicle density are inversely related during development. Skin cells seem to face a choice during formation: develop into hair follicles or sweat glands, with shared genetic pathways influencing both. As hair follicles decreased, sweat glands increased, creating the distinctive human pattern. This is the savanna hypothesis for human hairlessness. Climate change created open environments. Our ancestors moved into those environments, adopting survival strategies that required sustained daytime activity. Fur became a liability rather than an asset. Natural selection favoured hairlessness combined with enhanced sweating. The individuals who could stay coolest while active had the greatest survival and reproductive success. Over perhaps 1 million years, this pressure transformed a furry ape into a naked one. The evidence supporting this hypothesis is substantial. The timing works, with major hair loss occurring during the same period when our ancestors were definitely living in more open environments and showing skeletal adaptations for sustained walking and running. The geographic origin fits, with human hairlessness evolving in Africa, where savanna conditions would have created the strongest thermal stress. The correlation with bipedalism makes sense, two adaptations working together to enable daytime activity in hot exposed conditions. And most compellingly, modern humans really are exceptional endurance athletes specifically under hot conditions. Compare human performance to other mammals at different temperatures. In cold or moderate conditions, many animals outperform us. A wolf can trot for hours at speeds we can't match. A horse can cover distances that would exhaust even trained human runners. But in hot conditions, above 90 degrees Fahrenheit, especially with high humidity, humans suddenly have an advantage. We can keep going when other mammals have to stop. Our hairless skin and copious sweating lets us dump heat efficiently, even in conditions where fur-covered animals are forced to rest. This capability enabled a hunting strategy that might have been crucial to early human survival: persistence hunting. The basic idea is simple: pick an animal, start chasing it. The animal, most likely something like an antelope or kudu, bolts, running at full speed until it's far ahead. You keep jogging. Eventually you catch up, the animal runs again. You keep jogging. Over and over for hours, sometimes all day. The animal is faster in short bursts, but it can't cool down while running. It has to stop, stand, and pant to lower its core temperature. You never have to stop. You're cooling continuously through sweat evaporating from bare skin. Eventually, after 6, 8, maybe 12 hours of pursuit, the animal collapses from heat exhaustion. Its cooling system has failed. Yours hasn't. You walk up and kill it with a spear or rock. This sounds brutal. It is, but it works. Modern hunter-gatherers in the Kalahari Desert still practice persistence hunting, running down kudu in midday heat when no other predator would dream of hunting. Studies have documented these hunts, measuring core temperatures of both hunters and prey. The kudu's temperature rises steadily, reaching dangerous levels of 107, 108 degrees. The human hunters, sweating profusely but continuously cooling, maintain safe core temperatures below 100 degrees. The persistence hunter doesn't outsprint the prey. He outwits the prey's cooling system, and recent research has validated that this wasn't some rare, unusual practice. A 2024 study documented 391 historical accounts of endurance pursuit hunting from cultures around the world: North America, Australia, Africa, even parts of Asia. Everywhere humans lived, at least some populations practiced some form of persistence hunting. The technique was widespread, successful, and probably ancient. This is the power of hairlessness combined with eccrine sweating. It turned humans into pursuit predators unlike any other mammal. We became the marathon runners of the animal kingdom, not the fastest but the most relentless, the ones who could keep going when everything else had to stop, and that ability to be active during midday heat, to walk and run for hours without rest, that fundamentally shaped human evolution. But here's the thing, as compelling as the savanna hypothesis is, as much evidence as supports it, it's probably not the complete story. Because hairlessness solved the overheating problem beautifully, but it created other problems, serious ones. Problems that we'll need to explore to fully understand why our ancestors went naked. There's a theory about human evolution that mainstream science really doesn't like. Not because it's completely crazy, but because it was promoted by non-scientists, ignored proper academic channels, and made claims that were far too sweeping. The aquatic ape hypothesis. The idea that sometime in our evolutionary past, our ancestors spent significant time in water, and that this aquatic phase explains many peculiar human features, including our hairlessness. Now, before you dismiss this entirely, before you write it off as fringe pseudoscience, let me be clear about something. The strong version of this hypothesis, the one claiming humans are basically aquatic apes who evolved in water for millions of years, that's been thoroughly rejected by the scientific community. And for good reasons. The fossil evidence doesn't support it. The timeline doesn't work. Many of the supposed aquatic adaptations can be explained other ways. But here's what's interesting. If you strip away the overreach, if you look at the more modest claim that our ancestors spent significant time in and around water, exploiting aquatic resources, wading through shallows, that version actually has some intriguing evidence worth examining. And it might help explain hairlessness in ways that complement, rather than contradict, the savanna hypothesis. Because evolution doesn't demand single causes. Multiple environmental pressures can work together, each one pushing a species in the same direction for different reasons. Let's start with the most obvious similarity between humans and truly aquatic mammals. We're both essentially hairless. Whales, dolphins, porpoises, all marine mammals, they've lost their fur, not because they're overheating on savannas, but because fur is worse than useless in water. Get thick fur wet and it becomes a nightmare. It loses all insulating properties because water conducts heat away from the body about 25 times faster than air does. Wet fur won't trap the necessary layer of insulating air. It becomes matted, heavy, creates enormous drag when swimming, and takes forever to dry. Any mammal spending serious time in water faces strong selection pressure to lose its fur. But aquatic mammals didn't just lose their fur and call it done. They evolved something to replace it. Subcutaneous fat, a thick layer of fat directly beneath the skin, providing insulation that works in water. Seals have it, whales have it, manatees, walruses, hippos, any mammal spending substantial time in water has this fat layer. And here's the uncomfortable question for the savanna-only hypothesis. Why do humans have it? Look at other terrestrial mammals. Chimpanzees, gorillas, baboons, they're all skin and muscle, almost no subcutaneous fat. Their skin lies right against their muscle tissue with minimal padding. Even lean chimps and gorillas, the ones in peak physical condition, they don't have that layer of fat between skin and muscle that's so characteristic of humans. But humans, even lean athletic humans, have substantial subcutaneous fat. We're born chubby. Human babies come into the world with about 15% body fat, far higher than any other primate infant. That baby fat serves a purpose, insulating newborns who can't regulate their own temperature yet. But why so much more than other primates? And it's not just babies. Adult humans maintain higher levels of subcutaneous fat than any other ape, even when we're in excellent physical condition. Athletes with six-pack abs and defined muscles still have more fat between their skin and muscles than a chimpanzee does. This fat distribution, this emphasis on subcutaneous rather than visceral fat, it looks suspiciously like the pattern seen in semi-aquatic mammals. Now, the mainstream explanation is that this fat helps with energy storage, that it's an adaptation to unpredictable food supplies, that it buffers us against periods of scarcity, and that's probably part of the story. But it doesn't fully explain why we specifically have subcutaneous fat rather than visceral fat around our organs, which would also work for energy storage. The subcutaneous pattern, the all-over-the-body insulation layer, that looks like an aquatic adaptation. Then there's breath control. This one is weird when you really think about it. You're reading this, and you can hold your breath right now. You can consciously decide to stop breathing, hold for 30 seconds, a minute, maybe longer if you've practiced. This seems normal because you've been able to do it your entire life, but it's not normal for primates. Try to teach a chimpanzee to hold its breath. You can't. Chimps can't consciously control their breathing. They breathe automatically, reflexively, and can't override that reflex on command. But human infants, brand new babies who've never been in water before, they have something called the bradycardic response. Dunk a newborn in water, and they instinctively hold their breath. Their heart rate slows, blood flow redirects to vital organs. This is the mammalian diving reflex, and it's strongest in aquatic and semi-aquatic species. Seals have it, otters have it, hippos have it, humans have it, chimpanzees barely have it at all. Adult humans can train themselves to hold their breath for remarkable periods. Free divers regularly go 4, 5, even 10 minutes without breathing. The current world record is over 24 minutes. Now, part of this is training, mental discipline, techniques for saturating blood with oxygen beforehand. But the basic capability, the ability to consciously suppress the breathing reflex, to redirect blood flow during breath holding, to tolerate rising CO2 levels without panicking, that's unusual for a terrestrial mammal. That's the kind of capability you'd expect in an animal that regularly submerges. Then consider our body shape, particularly our legs. Human legs are proportionally longer than those of any other ape. We have a high leg length to body length ratio. Why? The standard explanation is that long legs are efficient for walking and running long distances. And that's true, but long legs are also efficient for wading through water. Stand a human, a chimpanzee, and a gorilla in chest-deep water. The chimp and gorilla panic, struggling to keep their heads above water, fighting to get back to land. The human instinctively stands upright, walks forward comfortably, uses the water to support their body weight. Our proportions seem optimized for wading in a way that other apes' proportions aren't. And look at our hands. Human fingers have webbing, actual membranous connections between the bases of each finger. Not dramatic webbing like a duck's foot, but it's definitely there. Other great apes don't have this. Their fingers are separated almost completely to the base. Why would humans have vestigial webbing if we never spent time in water? It serves no function on land, but it would make sense if our ancestors spent enough time swimming or wading, that even slight webbing provided some swimming advantage. Here's another strange one. Human babies are natural swimmers. From birth, they can coordinate their limbs in a swimming motion. They're comfortable in water. They seem to instinctively understand how to move through it. Put a newborn chimp in water, and it panics, flails, has no idea what to do. Put a newborn human in water, and it looks surprisingly competent, at least until they're a few months old and lose the reflex. Why would human babies have swimming reflexes if our ancestors never needed them? Now, none of these observations prove humans had an aquatic phase. Each one, taken individually, can be explained other ways or dismissed as coincidental. The subcutaneous fat might be about energy storage. The breath control might be a byproduct of speech evolution, which requires precise voluntary control of breathing. The long legs might be purely about terrestrial locomotion. The finger webbing might be a developmental quirk. The swimming reflex might be ancestral, inherited from much earlier mammals. But here's where the aquatic hypothesis gets interesting if you tone down the claims. What if human ancestors didn't live in water for millions of years, but did spend significant time exploiting aquatic resources? Wading through shallows collecting shellfish, diving for food in tidal pools, crossing rivers and streams, using water as refuge from land predators. Not being aquatic apes, but being comfortable around water in ways that other apes weren't. The archaeological evidence actually supports this more modest claim. Shell middens, massive piles of discarded shellfish shells, appear at early human sites going back hundreds of thousands of years. Coastal populations clearly relied heavily on marine resources. Some of the oldest known human settlements are along ancient coastlines, and there's good reason to think aquatic foods were important for human evolution. Shellfish, fish, aquatic plants, they're all rich in omega-3 fatty acids and iodine, nutrients that are crucial for brain development. Some researchers think access to these aquatic nutrients helped fuel the dramatic expansion of brain size in human evolution. And here's a critical point. During the Pleistocene ice ages, when glaciers locked up enormous amounts of water, sea levels were 300 to 400 feet lower than today. Vast areas of continental shelf that are now underwater were exposed land. The shores of Africa during the periods when humans were losing their fur looked nothing like modern African coasts. There were enormous shallow lagoons, estuaries, mangrove forests, all rich with aquatic resources. Our ancestors could have been exploiting these environments extensively without ever being aquatic apes, in the way the strong hypothesis claims. Imagine an early human population living along one of these ancient shorelines. They wade through shallows collecting shellfish, maybe diving in deeper water for sea urchins or catching fish in tidal pools. They're not swimming for hours or living in the water, but they're wet a lot. They're in and out of water multiple times per day. In this environment, fur becomes a serious liability. It's constantly wet, never fully dries, creates chafing and skin problems, harbours bacteria and fungi in the damp. Meanwhile, hairless skin dries quickly, doesn't trap moisture against the body, is much more hygienic in a semi-aquatic lifestyle. This could work together with the savanna adaptation. During dry seasons, these populations spread inland, foraging and hunting across grasslands. The hairlessness that evolved partly for aquatic living also helps them stay cool during sustained activity in hot open environments. During wet seasons or in coastal areas, they return to exploiting aquatic resources. The hairlessness that helps with heat dissipation on land also helps with hygiene and comfort in and around water. Multiple environmental pressures, all favouring the same adaptation for slightly different reasons. The scientific community's rejection of the aquatic ape hypothesis was primarily about the strong version, the one claiming a fully aquatic phase lasting millions of years. That version really doesn't hold up. There are no fossils of semi-aquatic hominins showing clear aquatic specializations, no skeletal features indicating extensive swimming, no adaptations like we see in actual aquatic mammals, things like streamlined body shapes, modified limbs for swimming, salt glands for excreting excess salt. The strong version overreached badly. But the moderate version, the idea that water played a significant role in human evolution alongside terrestrial adaptations, that's increasingly accepted. Humans probably didn't evolve in water, but they almost certainly evolved near water, exploiting aquatic resources, comfortable wading and swimming in ways that other apes weren't. And this relationship with water might have contributed to hair loss, as one of several selective pressures all pointing in the same direction. There's even some genetic evidence supporting this. Studies of populations that have lived by water for thousands of years show specific adaptations for diving and underwater foraging. The Bajau people of Southeast Asia, who spend up to 5 hours per day underwater fishing, have evolved larger spleens that store oxygenated blood, allowing longer dive times. This suggests humans can adapt to aquatic lifestyles relatively quickly, and such adaptations might have occurred repeatedly throughout our evolutionary history, wherever populations heavily exploited marine resources. So here's the balanced view. Humans probably aren't descended from aquatic apes who lived in water for millions of years. That claim is almost certainly wrong. But our ancestors probably weren't purely terrestrial savanna dwellers either. They were likely comfortable in multiple environments, including in and around water. They exploited resources from forests, woodlands, grasslands, and aquatic habitats. They were generalists, adaptable, willing to use whatever environment offered food and safety. And hairlessness. It probably evolved because it was advantageous in multiple contexts. Better cooling on hot grasslands during persistence hunting, better hygiene and comfort when spending time in and around water. Reduce parasite burden, which we'll explore in the next chapter. Improve social communication through more visible skin, which we'll also get to. Evolution doesn't demand single explanations. Multiple pressures can converge on the same solution, each one adding to the selective advantage of losing fur. The aquatic hypothesis, in its reasonable form, reminds us that human evolution was complex, multifaceted, influenced by many different environments and challenges. Our ancestors weren't locked into a single lifestyle or habitat. They were flexible, innovative, willing to exploit any resources available. and some of those resources were in the water. Not enough to make us truly aquatic, but enough to potentially influence our evolution in subtle but important ways, including possibly contributing to the loss of fur that makes us so strange among primates. The naked apes who can run for hours under the hot sun and also feel perfectly comfortable wading through cool water. Two abilities that seem contradictory, but might both have shaped our peculiar hairlessness. Let's talk about something deeply unpleasant, something that makes your skin crawl just thinking about it. The creatures that lived in your ancestors' fur, tiny arthropods with hooked legs designed to cling to hair shafts, mouthparts adapted for piercing skin and sucking blood, bodies carrying bacteria, viruses and parasitic organisms that could kill you just as effectively as any predator. We're talking about ticks, lice, fleas, mites, the ectoparasites that every furred mammal carries and that might have been the driving force behind human hairlessness. Because here's something most people don't realise. Parasites are one of the strongest selective pressures in evolution. Stronger than predators in many cases. A lion might kill you once. A tick-borne disease can kill hundreds over years before anyone figures out how to avoid it. Parasites are invisible, ubiquitous, and absolutely relentless. And for a fur-covered primate living in tropical Africa, they were everywhere. Close your eyes and imagine you're one of those early hominins we've been discussing. You're covered in thick body hair, living in groups of maybe 30 or 40 individuals sleeping close together for warmth and safety. Now zoom in microscopically to that fur layer. It's not just hair, it's an ecosystem. Dozens, maybe hundreds of lice crawling through the dense hair on your scalp and body, laying eggs that hatch into more lice. Ticks buried deep in your fur, latched onto your skin, feeding for days at a time, their bodies swelling with your blood. Fleas jumping from individual to individual whenever your group huddles together. Mites living in your hair follicles, feeding on oils and dead skin cells. This isn't science fiction or exaggeration. This is the normal condition for most furred mammals. Modern primates in equatorial Africa carry incredible parasite loads. Studies of wild chimpanzees have found individuals hosting dozens of different ectoparasite species simultaneously. Some chimps have over 100 ticks on their bodies at once. Gorillas can carry even more. It's just part of life for a fur-covered animal in the tropics. And these parasites aren't just annoying, they're deadly. Modern medicine has made us forget how dangerous parasites actually are. But before antibiotics and pest control, ectoparasite-borne diseases killed millions. Typhus, spread by body lice, has wiped out entire armies. Plague, transmitted by fleas, killed a third of Europe's population during the Black Death. Lyme disease, carried by ticks, can damage your heart, nervous system, and joints if untreated. Rocky Mountain spotted fever, also tick-borne, kills about 5% of infected people even with modern treatment. In tropical Africa, where our ancestors evolved, the parasite diversity is staggering. There are tick species that specifically target primates, lice species adapted to living in ape fur, mites that cause mange and secondary infections. Each one a potential disease vector, each one reducing the host's fitness, each one creating selection pressure for any adaptation that reduces parasite load. Now, imagine you're born with a mutation that gives you slightly less body hair than your peers. Maybe your fur is a bit thinner, a bit shorter, not quite as dense. This makes you more visible to predators, sure. It makes you less protected from thorns and sharp grasses. But it has one massive advantage. Parasites hate it. Ticks can't hide as easily in sparse hair. They're more visible, easier to spot and remove before they burrow in and start feeding. Lice have fewer hair shafts to cling to, making it harder for them to establish large populations. Your overall parasite load drops significantly. What does this mean for survival? You're healthier. You have fewer infections. You're not constantly dealing with the itching, inflammation, and energy drain that heavy parasite loads create. You're not losing blood to ticks or risking deadly diseases from lice-borne bacteria. In a world where disease is one of the leading causes of death, especially in children, being less parasitized is an enormous advantage. You're more likely to survive to reproductive age. Your children are more likely to survive because they inherit your reduced hairiness and lower parasite burden. Over generations, the hairless trait spreads. Not because anyone understands parasitology or germ theory, simply because the less hairy individuals are, on average, healthier and more successful at reproducing. Natural selection doesn't care why something works. It only cares that it does. This is the ectoparasite hypothesis for human hairlessness, and there's substantial evidence supporting it. Let's start with a simple observation. When modern humans do get body lice, where do they live? Not on our bodies directly, because we don't have enough hair for them anymore. Body lice in modern humans live in clothing. They've adapted to a new habitat because their original habitat, our fur, disappeared. Scientists have actually studied the evolution of human lice, and it tells a fascinating story. There are 3 types of lice that parasitize humans: head lice, which live in scalp hair; pubic lice, which are actually more closely related to gorilla lice than to human head lice, suggesting we acquired them relatively recently from contact with gorillas, probably through butchering or sleeping in their nests; and body lice, which live in clothing. When researchers sequenced the DNA of these lice species and used molecular clock analysis to estimate when they diverge from each other, they found something remarkable. Body lice split from head lice somewhere between 83,000 and 170,000 years ago. That's when body lice evolved as a distinct species adapted to living in clothing rather than body hair, which means that's approximately when humans started wearing clothing regularly enough for lice to specialize in that new habitat. But wait, if body lice only evolved 83,000 to 170,000 years ago, that means there was no body hair for them to live in before that, which means humans had already lost most of their body hair by that point. The lice timeline gives us a minimum date for human hairlessness. We were already naked, or nearly so, by the time we invented regular clothing use. This creates an interesting scenario. Our ancestors lost their body hair, presumably at least partly to reduce parasites. This worked, dramatically reducing lice populations because lice need hair to survive, but humans retained head hair, and head lice never went extinct. They just stayed confined to the scalp where they could still thrive. Then, much later, when humans invented clothing, lice found a new habitat. Body lice evolved from head lice, adapting to live in the fibers of clothing instead of body hair. Humans traded fur parasites for clothing parasites, though presumably the clothing could be cleaned or replaced, giving us more control over the parasite burden. But lice are just one type of ectoparasite. Ticks are arguably more dangerous because they're much better disease vectors. Modern tick-borne diseases include Lyme disease, Rocky Mountain spotted fever, ehrlichiosis, anaplasmosis, babesiosis, and many others. Some of these can be fatal even with treatment. All of them can cause serious health problems, and in the prehistoric world without antibiotics, tick-borne diseases would have been even more devastating. Ticks are particularly problematic for furred animals because they can burrow deep into the fur layer, making them hard to detect and remove. A tick feeding on a chimpanzee can hide completely in the dense body hair, only visible if you part the fur and look carefully. But a tick on a human is immediately obvious. Our naked skin provides no cover. We can spot ticks quickly and remove them before they have had time to transmit disease. There's actually fascinating recent research on this. A 2021 study proposed what they call the tick-based hypothesis for human-chimpanzee divergence. The researchers argued that when our ancestors moved from forests into more open woodland and grassland environments, they encountered much higher tick loads. Forest canopy-dwelling primates don't encounter many ticks, but ground-dwelling animals in open habitats with tall grasses, that's prime tick territory. Ticks climb grass stems and drop onto passing animals. The hypothesis suggests our ancestors faced a choice. Deal with increased tick loads by evolving enhanced grooming behavior, like chimpanzees did, spending hours each day meticulously searching through each other's fur for parasites. Or lose the fur entirely, making ticks immediately visible and easy to remove. Chimpanzees went one direction, spending huge amounts of time on social grooming. Humans went the other, shedding the fur that harboured parasites. And the evidence shows this actually happened. Modern humans in traditional societies spend much less time on anti-parasite grooming than other primates do. A study of 6 traditional small-scale societies found they spent only about 0.8% of their daily activity on parasite removal grooming. Chimpanzees spend 10 to 20% of their day grooming. That's a massive difference. Humans don't need to groom as much because visual inspection of naked skin is so much more efficient than searching through fur. But there's another dimension to the parasite story that's often overlooked: group size. As human ancestors began living in larger groups, parasite transmission became a much more serious problem. Small groups that move frequently don't accumulate parasites as badly. There's limited opportunity for parasites to spread, and abandoned sleeping sites leave parasites behind. But large groups staying in the same location for extended periods, that's when parasite problems explode. Think about it from the parasite's perspective. You're a louse or a flea. In a small group of 15 chimps that moves to a new sleeping site every few nights, you have limited hosts and your eggs might get left behind when the group moves. But in a group of 50 to 100 early humans staying in the same general area for weeks or months, you're in paradise. Plenty of hosts in close contact, stable sleeping areas where your eggs can hatch and find new hosts. Parasite populations can boom. This created increasingly strong selection for any adaptation that reduced parasite vulnerability. And hairlessness is one of the most effective anti-parasite adaptations possible for a mammal. It doesn't just reduce parasite populations, it makes parasite management exponentially easier. A hairless human can visually inspect their entire body surface in minutes. A furred primate needs hours of grooming by others to achieve the same level of parasite control. There's even evidence that humans evolved psychological responses specifically tuned to ectoparasites. Research shows that people react with disgust and skin-crawling sensations specifically to stimuli associated with ectoparasites, and these reactions are different from the disgust responses to pathogens or contamination. Show someone images of ticks, lice or spiders crawling on skin, and they report intense itching sensations and engage in self-grooming behavior, even though they're not actually infested. This suggests our brains evolved specific detection and response systems for ectoparasites, systems that would have been crucial when parasite loads were much higher in our evolutionary past, and modern evidence continues to support the connection between hair and parasites. Studies of various mammal species consistently show that species living in large social groups with thick fur suffer much higher parasite burdens than solitary species or hairless species. Bats living in caves with thousands of individuals are absolutely covered in parasites. Prairie dogs in large colonies have high tick and flea loads. Primates living in big troops show more parasite diversity and density than solitary primates. Humans were moving toward larger groups, denser populations, more social complexity. Every step in that direction increased the selective pressure against body hair. Every generation, the individuals with less hair were slightly healthier, their children survived at slightly higher rates. Over hundreds of thousands of years, this cumulative pressure stripped away the fur that our ancestors had carried for millions of years. Now, here's the critical insight. The parasite hypothesis doesn't contradict the savanna hypothesis or the aquatic influences. They all work together. Hairlessness provides better cooling for sustained activity and heat. Check. Hairlessness provides better hygiene in and around water. Check. Hairlessness dramatically reduces parasite loads and disease transmission. Also, check. Multiple environmental pressures, multiple survival challenges, all pointing toward the same solution. Lose the fur. Evolution loves solutions that solve multiple problems simultaneously. An adaptation that only provides one benefit in one specific context might not spread very effectively. But an adaptation that provides advantages in multiple contexts, that helps you in several different ways, that spreads quickly and becomes fixed in a population. Hairlessness was that kind of adaptation. Our ancestors faced overheating during persistence hunting. Hairlessness helped. They faced hygiene challenges when exploiting aquatic resources. Hairlessness helped. They faced crushing parasite loads that killed children and weakened adults. Hairlessness helped enormously. The selective pressure came from multiple directions, all pushing the same way, making hairlessness one of the most advantageous adaptations in human evolution. But hairlessness created its own problems, serious ones. When you shed your fur, you also shed your protection against UV radiation. You lose your insulation against cold. You become vulnerable to abrasions, thorns, insect bites. These vulnerabilities had to be addressed, or they would have prevented hairlessness from spreading. Which means we need to look at the cascade of adaptations that hairlessness triggered, the solutions our ancestors evolved to deal with the problems that nakedness created. Starting with the most immediate problem, exposed skin under the brutal African sun. Imagine peeling off a thick winter coat on the first warm day of spring. That immediate feeling of liberation, of lightness, of freedom. Now imagine you're standing in the Sahara Desert at noon, without sunscreen, without a hat, without any protection whatsoever. Within minutes your exposed skin starts to burn. Within an hour you're dealing with serious sunburn, push it further, and you're looking at sun poisoning, blistering, potential skin cancer down the line. This is what our ancestors faced the moment they started losing their fur, and it could have killed them before hairlessness ever provided any advantages. UV radiation isn't just uncomfortable, it's directly damaging to DNA. The ultraviolet photons from sunlight strike the DNA molecules in your skin cells and create lesions, molecular kinks that prevent the DNA from replicating correctly. Your cells have repair mechanisms for this damage, enzymes that patrol DNA constantly looking for UV-induced lesions and fixing them, but there's a limit to how much damage can be repaired. Overwhelm the system with too much UV exposure, and mutations start accumulating. Some of those mutations turn cells cancerous, others damage genes critical for cellular function. But skin cancer isn't actually the main problem from an evolutionary perspective. Most skin cancers develop later in life, after people have already reproduced. Natural selection doesn't care much about things that kill you after your reproductive years. What selection does care about intensely is reproductive success. And this is where UV radiation becomes truly dangerous, because it destroys folate. Folate, also known as folic acid or vitamin B9, is absolutely critical for cell division, DNA synthesis, and cellular repair. It's involved in creating new cells, which means it's essential for growth, healing, and reproduction. During pregnancy, folate is crucial for fetal neural tube development. Low folate levels in pregnant women lead to devastating birth defects, neural tube defects like spina bifida, where the spinal cord doesn't form properly. These defects cause stillbirths, infant mortality, severe disabilities. In evolutionary terms, they mean reproductive failure, and here's the terrifying part. UV radiation breaks down folate. The same ultraviolet photons that damage DNA also degrade folate molecules circulating in blood vessels near the skin surface. Expose pale skin to intense sunlight, and folate levels drop measurably. In men, low folate reduces sperm count and sperm quality, directly impacting fertility. In women, especially pregnant women, low folate means higher rates of miscarriage, birth defects, and infant death. This creates an immediate catastrophic problem for hairless hominins living near the equator. Lose your fur, expose your pale skin to tropical African sun, and your folate levels crash. Your reproductive success plummets. Natural selection would hammer any population that went hairless without simultaneously developing protection against UV radiation. The selective pressure would be enormous, immediate, and brutal. The solution was melanin. This is the dark pigment that gives skin its color, and it's nature's sunscreen. Melanin molecules absorb UV radiation, preventing those harmful photons from penetrating deep into the skin and damaging DNA or breaking down folate. The more melanin you have in your skin, the darker your skin appears and the better protected you are from UV damage. And we know exactly when this adaptation appeared because scientists have analysed the genetics. The MC1R gene, melanocortin-1 receptor, is one of the major genes controlling melanin production in human skin. When researchers sequenced this gene across different human populations and used molecular clock analysis to estimate when changes occurred, they found something remarkable. The versions of MC1R associated with very dark skin, the variants found in African populations, show evidence of intense purifying selection beginning around 1.2 million years ago. Purifying selection is what geneticists call it, when natural selection ruthlessly eliminates any variation from an optimal gene sequence. It means individuals with different versions of the gene had significantly lower reproductive success. Their children were less likely to survive. Over time, only the optimal version remains in the population because anything else is selected against so strongly. The MC1R gene in African populations shows this pattern, almost no variation, suggesting that dark skin became absolutely mandatory for survival. 1.2 million years ago. That's right around when our ancestors were losing most of their body hair. The timing is too perfect to be coincidental. As fur disappeared, dark skin had to evolve immediately, or the hairless individuals would have suffered catastrophic reproductive failure. This wasn't a gradual process spread over millions of years. This was evolution operating on emergency timescales, fixing a life-threatening problem as quickly as genetic changes can spread through a population. Think about what this means for the individuals involved. Imagine you're an early human, maybe one of the first generations to be born mostly hairless. If you inherited genes for pale skin, you're in trouble. Your skin burns easily, you're constantly uncomfortable in the sun, and critically, your folate levels are lower than your darker-skinned peers. You have more miscarriages, more children born with defects, fewer healthy offspring overall. Meanwhile, individuals born with genes for darker skin are thriving. Their melanin-rich skin protects them, their folate levels remain stable, their children survive at higher rates. Over just a few thousand generations, perhaps 50,000 to 100,000 years, the population shifts from mostly pale-skinned to uniformly dark-skinned. Any gene variants that reduce melanin production in equatorial populations were eliminated. Dark skin wasn't just advantageous, it was mandatory. The fossil and genetic evidence suggests that by several 100,000 years ago, all humans living in Africa had very dark skin. Not tanned, but genetically dark, with high melanin content built into their baseline skin colour. This is why modern African populations show so little variation in the genes controlling dark pigmentation. The selection pressure was so strong, so consistent, that it eliminated variation. Everyone needed maximum melanin protection. There was no evolutionary room for lighter skin variants to persist. But melanin does more than just block UV radiation. It's also a remarkably sophisticated molecule with multiple protective functions. Melanin acts as an antioxidant, neutralizing harmful reactive oxygen species that UV exposure creates in skin cells. It scavenges free radicals that would otherwise damage cellular components. It even provides some protection against certain bacterial and fungal infections. Dark skin isn't just a sun hat, it's a multifunctional protective system. There are actually two main types of melanin in human skin. Eumelanin, which is dark brown to black and provides excellent UV protection, and pheomelanin, which is yellow to reddish and provides much less protection. People with very dark skin produce predominantly eumelanin. People with lighter skin produce more pheomelanin relative to eumelanin, which is why they're more vulnerable to UV damage. The production of these melanins is controlled by a network of genes working together. MC1R is the master regulator, but other genes like TIA, TRP1, OCA2, and SLC24A5 also contribute to determining skin colour. Mutations in any of these genes can lighten skin, but in African populations living near the equator, the versions associated with maximum melanin production were strongly selected for across all these genes simultaneously. Now here's where the story gets really interesting. Because humans didn't stay in equatorial Africa, starting around 70,000 to 100,000 years ago, modern humans began migrating out of Africa, spreading across the Middle East, into Asia, eventually reaching Europe and beyond. And as they moved into higher latitudes, farther from the equator, the rules changed completely. In equatorial regions, UV radiation is intense year-round. The sun passes almost directly overhead, meaning sunlight travels through minimal atmosphere before hitting Earth's surface. Maximum UV exposure, maximum need for melanin protection. But move to higher latitudes, 40, 50, 60 degrees north or south, and UV levels drop dramatically. The sun stays lower in the sky, light passes through more atmosphere, and much of the UV gets absorbed or scattered before reaching the ground. Initially, this seems like it wouldn't matter. Dark skin protects against UV, so even if UV levels are lower, the protection is still useful, right? Except there's a problem, a critical problem. Your skin needs some UV exposure to synthesize vitamin D. Vitamin D is essential for calcium absorption, bone development, immune function, and dozens of other biological processes. Without adequate vitamin D, you get rickets, a disease that causes bone deformities, weakened skeleton, and reduced reproductive success. Women with rickets often have pelvic deformities that make childbirth difficult or impossible. Before modern medicine, this meant death for both mother and child. Even mild vitamin D deficiency increases susceptibility to infections, weakens bones, and impairs normal growth. Your body manufactures vitamin D in skin cells using UV radiation as the energy source. UVB photons strike a cholesterol derivative in your skin and convert it to pre-vitamin D3, which then transforms into active vitamin D. It's an elegant system, as long as you get enough sun exposure. But here's the problem. Melanin blocks the same UV radiation needed for vitamin D synthesis. In equatorial regions with intense year-round sun, even very dark skin allows enough UV through to produce adequate vitamin D. But in northern Europe, where winter days are short and the sun barely rises above the horizon, where UV levels are a fraction of what they are at the equator, dark skin becomes a liability. The melanin that protects against UV damage now blocks the limited UV needed for vitamin D production. People with dark skin living at high latitudes face chronic vitamin D deficiency. Natural selection doesn't tolerate this. In low UV environments, individuals with lighter skin had a massive advantage. They could produce vitamin D more efficiently, maintain healthier bones, have better immune function, survive winter better. Their children were healthier, their reproduction more successful. Over thousands of generations, populations living at high latitudes evolved progressively lighter skin, and the genetic evidence shows this happened independently in multiple populations. Europeans, East Asians, and some Central Asian populations all evolved lighter skin, but they did it through different genetic mutations. Europeans have specific variants in SLC24A5 and SLC45A2 that reduce melanin production. East Asians have different variants in other genes. This is convergent evolution, multiple populations independently solving the same problem through different genetic routes. The fact that different populations use different genetic solutions tells us the selective pressure was incredibly strong. Evolution found multiple ways to lighten skin because it absolutely had to. Any population living at high latitudes without adequate vitamin D production would suffer reduced fitness. The evolutionary pressure was strong enough that it drove rapid genetic change in multiple populations simultaneously, and the timing of these changes is remarkably recent. The gene variants associated with pale skin in Europeans probably emerged within the last 30,000 to 50,000 years. Some researchers think it might have happened even more recently, possibly as late as 10,000 years ago, accelerated by the adoption of agriculture. Agricultural diets provided less vitamin D than hunter-gatherer diets rich in fish and organ meats, increasing the selective pressure for lighter skin that could synthesize vitamin D more efficiently. This creates a beautiful example of local adaptation. Human skin color maps almost perfectly to UV radiation levels at different latitudes. Darkest skin at the equator, where UV is strongest, progressively lighter skin at higher latitudes where UV is weaker. The correlation is so strong it's almost a one-to-one relationship. Measure the UV intensity at a location, and you can predict the skin color of populations that have lived there for thousands of years. But this also means that human skin color is purely an environmental adaptation with no deeper significance. It's a tan. An evolutionary tan, fixed in our genes, but fundamentally just an adaptation to local UV levels. The same way Arctic foxes have white fur and desert foxes have tan fur, human populations evolved different skin colors based on their environment. It's about vitamin D synthesis and folate protection, nothing more. The tragedy is that these superficial adaptations became the basis for racial categorization and discrimination. Skin color differences that evolved over just the last few tens of thousands of years, that have no correlation with intelligence, personality, or capability, that are purely about UV protection and vitamin D synthesis, became justification for slavery, genocide, and systemic oppression. It's a profound misunderstanding of what skin color actually represents. But from an evolutionary perspective, the melanin story reveals how quickly humans can adapt to new environments. Move from equatorial Africa to northern Europe, a shift of about 40 to 50 degrees latitude, and within 30,000 to 50,000 years, maybe less, populations evolved from very dark skin to very pale skin. That's remarkably fast evolution, suggesting the selective pressure was intense, and we're still evolving. Human populations continue to mix, and skin color continues to change as people move between different UV environments. Someone of Northern European descent living in Australia faces increased skin cancer risk because their pale skin isn't adapted to intense Australian sun. Someone of African descent living in Scandinavia faces potential vitamin D deficiency because their dark skin isn't adapted to limited northern sun. Modern technology, sunscreen and vitamin D supplements, allows us to override these evolutionary mismatches, but they still exist. The melanin shield, the rapid evolution of dark skin to protect hairless humans from UV damage, was one of the most critical adaptations in human evolution. Without it, hairlessness would have been impossible. Our ancestors would have suffered devastating reproductive failure from folate depletion long before hairlessness could provide any cooling or anti-parasite advantages. The evolution of dark skin and the evolution of hairlessness had to happen together, each enabling the other, creating a package of adaptations that transformed our ancestors from furred apes into naked humans. But even with dark skin protecting them from UV damage, our hairless ancestors still faced enormous challenges. Challenges that would force them to become inventors. There's something you do every day without thinking about it. Something so automatic, so deeply wired into your brain that you barely notice you're doing it. You read faces. Within milliseconds of seeing someone, you extract massive amounts of information from their facial expression. Are they happy, sad, angry, frightened? Are they healthy or sick, stressed or relaxed, trustworthy or dangerous? You make these assessments instantly, unconsciously, using subtle cues from muscle movements, skin color changes, and tiny micro-expressions that flash across someone's face for fractions of a second. Now try to imagine doing this through fur. Try reading the emotional state of a chimpanzee just by looking at its face. It's much harder, isn't it? The fur obscures the fine details. You can't see the subtle color changes that signal emotional states. You can't detect the small muscle movements that reveal what someone is thinking or feeling. Fur is like a mask, hiding the rich information that naked skin displays. This is one of the most overlooked consequences of human hairlessness. When our ancestors lost their fur, they didn't just lose protection and insulation, they gained a communication system unlike anything in the primate world. Naked skin, especially facial skin, became a billboard advertising emotional state, health status, and social intentions. And this transparency might have been just as evolutionarily important as better cooling or reduced parasites. Let's start with the most obvious signal. Blushing. You know the feeling. Embarrassment, shame, attraction. Any strong emotional state with a social component, and blood rushes to your face. Your cheeks turn red, sometimes your whole face flushes. You can't control it, can't fake it, can't suppress it. It's an involuntary physiological response triggered by your autonomic nervous system. And it's uniquely human. Other primates don't blush. Or if they do, you can't see it through their fur. The reddening of skin caused by increased blood flow to facial blood vessels is completely hidden by the layer of hair covering their faces. But on naked human skin, blushing is immediately obvious to anyone looking at you. Charles Darwin called blushing the most peculiar and most human of all expressions. He was fascinated by it because it seemed to serve no practical purpose, and yet was universal across all human cultures. But blushing does serve a purpose. It's an honest signal. You can't fake a blush, which means when someone blushes, you know they're experiencing genuine emotional arousal related to social judgment. They're embarrassed about something. They're caught in a lie. They're attracted to someone. They're feeling guilty. The blush reveals their internal emotional state whether they want it to or not. And in small groups where reputation and trust are everything, where your survival depends on cooperation with others, honest signals of your emotional state are incredibly valuable. Imagine you're confronting someone in your group who you suspect stole food. They deny it verbally, claiming innocence, but their face flushes red as they speak. You know they're lying. The blush betrayed them. Or conversely, someone is falsely accused and their face stays normal, no flush, no signs of guilty arousal. You're more likely to believe their innocence. The presence or absence of blushing provides information that helps groups navigate social conflicts and maintain cooperation. But blushing is just the most dramatic example. Naked facial skin reveals dozens of more subtle signals. Pallor, the draining of blood from the face in response to fear or shock. When someone goes white, you know they've just experienced something frightening or disturbing. Feverish flush, the reddened appearance of someone fighting an infection. Jaundice, the yellowing of skin that indicates liver problems. Dark circles under the eyes revealing exhaustion or illness. Skin texture changes showing dehydration or poor nutrition. All of these signals would be invisible on a furred primate. But on naked human skin, they're obvious. And this creates what biologists call an honest signaling system. Unlike verbal communication where you can lie, your skin betrays your true physiological and emotional state. You can tell someone you're feeling fine, but if your skin shows signs of illness or stress, they'll know the truth. This honesty would have been crucial for our ancestors living in small groups, where everyone's survival depended on everyone else. You need to know if someone in your group is sick, because infectious diseases spread quickly in close quarters. You need to know if someone is stressed or frightened, because their fear might indicate danger nearby. You need to know if someone is lying about their loyalty or their actions, because betrayal in a survival situation could get people killed. Naked skin made all of this information visible, and it's not just faces. The entire body surface became a display. Look at someone's hands. Are they calloused and rough, indicating they do hard physical work? Are they trembling, revealing anxiety or stress? Are the fingernails healthy or damaged? What about posture and gait? Does someone move smoothly or awkwardly? These observations, made automatically by your visual system, provide information about health, age, physical capability, and emotional state. Hairlessness also enabled more sophisticated facial expressions. The human face has about 43 muscles dedicated to creating expressions. Many of these muscles are much more developed in humans than in other apes. We can move our eyebrows independently, wrinkle our foreheads, curl our lips in dozens of different ways, create subtle asymmetries that convey complex emotional states. Chimpanzees have many of the same facial muscles, but their expressions are harder to see through fur and less finely controlled. Evolution apparently favoured individuals who could display subtle, nuanced facial expressions and who could accurately read those expressions in others. This created a feedback loop. More expressive faces provided better social communication. Better readers of facial expressions gained social advantages. Both traits would have been selected for driving the evolution of an increasingly sophisticated facial expression system. And here's something remarkable. Facial expression recognition appears to be partly innate and partly learned. Babies can recognize basic emotional expressions like happiness and fear within months of being born, suggesting these are biologically prepared responses. But the ability to read subtle, complex expressions improves with experience. Children raised in environments with limited social interaction show impaired facial expression recognition. Your brain literally needs practice reading faces to become expert at it. This suggests that over evolutionary time, humans became increasingly dependent on facial communication. It wasn't just a nice bonus, it became essential for social functioning. A person who couldn't read facial expressions accurately would miss crucial social information, misinterpret others' intentions, fail to respond appropriately to social cues. They would be at a severe disadvantage in negotiating the complex social world that early humans inhabited. But there's another dimension to skin as communication medium: sexual selection. When choosing mates, being able to assess someone's health and genetic quality is critically important. You want to reproduce with someone who will produce healthy offspring, who has good genes to pass on. But how do you assess genetic quality in another person, especially in a world before medical science, before any understanding of genetics? Skin provides clues. Clear, unblemished skin suggests good health and absence of disease. Symmetric features indicate normal development without genetic problems or environmental stresses during growth. Smooth skin texture suggests adequate nutrition. The absence of scars, lesions, or parasitic infections indicates effective immune system and good hygiene. All of these are honestly signalled through naked skin in ways that would be hidden by fur. This created selection pressure for hairlessness through mate choice. If individuals could better assess potential mates' quality when those mates had less fur, then people might actively prefer less hairy partners. Over generations, this preference could drive further hair loss. The process would be self-reinforcing. Less hair allows better assessment. Better assessment leads to preferences for less hair. Preferences for less hair selects for even less hair. Some researchers think this sexual selection component was significant. The pattern of where humans retain hair versus where we lost it suggests sexual signaling might have played a role. We kept head hair, which in most human populations grows long and thick, providing a display feature that can be styled and modified. We kept pubic and armpit hair, which appears during puberty and coincides with sexual maturity, clearly marking an individual as reproductively capable. We kept facial hair in males, which is testosterone dependent and honestly signals male hormonal status and maturity. But we lost most of the body hair that covered our torsos, arms and legs. The hair that would have hidden skin quality indicators. It's an interesting pattern. Keep hair in locations where it can serve as a sexual signal or maturity indicator. Lose hair in locations where it would hide health and quality information. This suggests sexual selection and social signaling were working together with heat dissipation and parasite reduction to drive hairlessness. And there's one more aspect of skin as communication that deserves attention: tactile sensitivity. When you lose fur, your skin becomes much more sensitive to touch. Fur creates a barrier, dulling tactile sensations, but naked skin can feel the slightest touch, the gentlest breeze, subtle temperature variations. This enhanced sensitivity matters for social bonding. Think about the importance of touch in human relationships. Mothers holding infants, the physical contact that bonds parent and child. Friends hugging, lovers embracing, the role of physical affection in maintaining social connections. Touch is a powerful communication channel. It conveys comfort, affection, trust, desire, and it works much better on naked skin than through fur. Studies have shown that gentle touch triggers release of oxytocin, a hormone involved in social bonding and trust. The effect is stronger when touching bare skin than when touching through clothing. This suggests that naked skin enhanced the bonding effects of physical contact, strengthening social relationships in ways that would have been important for group cohesion. Early human groups needed strong social bonds to survive. Cooperation in hunting, sharing of food, collective child rearing, defense against predators and rival groups, all of this required trust and social cohesion. Physical contact through touching naked skin likely played a role in maintaining these bonds, especially between mothers and infants, but also among all group members. There's even research suggesting that human infants have stronger touch sensitivity than other primate infants, and that this sensitivity is crucial for normal social and emotional development. Babies who receive inadequate physical contact show impaired development in multiple domains. The importance of touch for human infants makes sense if hairlessness evolved partly to enhance tactile communication and bonding. So here's the picture that emerges. Hairlessness wasn't just about thermoregulation or parasite reduction. It transformed humans into highly visual social communicators. Naked skin became a display surface for emotional states, health status, genetic quality, all the information needed to navigate complex social environments. Facial expressions became more elaborate and easier to read. Sexual selection favored individuals with clear skin that honestly advertised their quality. Touch became a more powerful bonding mechanism. All of this would have reinforced the advantages of hairlessness. Better cooling and reduced parasites made hairlessness selectively advantageous in the first place. But once hair started disappearing, the communication and social benefits created additional selective pressure. Individuals with less hair could communicate more effectively, form stronger social bonds, assess potential mates more accurately. These social advantages added to the physiological advantages, accelerating the evolution toward complete hairlessness. But it also created new vulnerabilities. Naked skin isn't just more visible, it's more vulnerable. Without fur protection, our ancestors faced cold nights, thorny vegetation, stinging insects, all the physical hazards that fur had protected them from. These vulnerabilities should have been serious enough to prevent hairlessness from evolving, unless our ancestors found other solutions, technological solutions, solutions that would eventually transform them from clever apes into inventors of civilization. Here's a thought experiment. Take a modern human, strip them naked, and put them anywhere on Earth outside the tropics. No clothes, no shelter, no tools, nothing. Just bare skin and whatever natural resources they can find. How long do they survive? In temperate climates, maybe a few days before hypothermia sets in during the first cold night. In Arctic or subarctic regions, hours at most. Even in warm deserts, the combination of intense daytime heat and cold nights would be lethal within days. Humans are uniquely vulnerable among mammals. We have no fur for insulation. We can't burrow underground like many small mammals. We don't hibernate. We can't migrate thousands of miles like birds. We're naked, relatively slow, lacking natural weapons or armor, and completely dependent on our intelligence to survive in most of Earth's environments. Our hairlessness should have confined us to a narrow tropical band where temperatures stay warm year-round. Instead, humans live everywhere, from the Arctic to the Amazon, from deserts to rainforests, from sea level to high mountains. How is this possible? Because vulnerability drove innovation. The moment our ancestors started losing their fur, they had to become inventors or die. And this necessity, this absolute requirement for technological solutions to biological vulnerabilities, might have been one of the most important factors shaping human evolution. Hairlessness didn't just happen alongside human intelligence. It might have driven the development of human intelligence. Let's start with the most obvious problem: cold. Even in tropical Africa, where hairlessness evolved, temperatures drop at night. Daytime highs might reach 90 degrees Fahrenheit, but nighttime lows can fall to 60, or even 50 degrees. That might not sound cold to someone from a northern climate, but remember, you're generating less metabolic heat when sleeping. Your basal metabolic rate, the heat your resting body produces, is only about 70 to 100 watts. Without insulation, you're losing heat to the environment continuously. On a 60-degree night, a naked human can easily develop hypothermia while sleeping. A fur-covered primate doesn't worry about this. Their coat provides insulation that traps a layer of warm air next to the skin. Chimpanzees and gorillas sleep in the open or in simple nests, completely comfortable at temperatures that would be dangerous for naked humans. But our hairless ancestors faced a choice. Either avoid cold environments entirely, or figure out how to stay warm. They figured it out. Multiple solutions, actually. The most obvious was fire. Control of fire, the ability to create and maintain flames for warmth, light, and cooking. This is considered one of the defining achievements of human evolution, and it might have been directly driven by hairlessness. When you can't stay warm without external heat sources, fire stops being optional. It becomes essential for survival. The archaeological evidence for fire use is frustratingly sparse for the early periods, partly because fire doesn't preserve well. Charcoal and ash can survive under the right conditions, but often the evidence degrades or gets scattered. What we do have suggests occasional fire use going back perhaps 1.5 to 2 million years, right around when major hair loss was probably occurring. But habitual systematic fire use, the kind where every human group maintains fire continuously, that probably didn't become universal until much later, maybe 400,000 years ago. This timeline actually makes sense if hairlessness was still incomplete earlier. Our ancestors were gradually losing hair over hundreds of thousands of years, not all at once. Early hominins with partial hairlessness might have managed with occasional fire use during especially cold periods. But as hairlessness became more complete, fire went from useful to essential. Groups that couldn't maintain fire would have been confined to warm areas. Groups that mastered fire could expand into temperate regions, exploit resources unavailable to other primates, survive seasonal cold, and fire doesn't just provide warmth, it provides light, extending the useful day beyond sunset. It provides protection from predators, most of which fear fire instinctively. It enables cooking, which makes many foods more digestible and safer by killing parasites and bacteria. Fire is a multi-purpose technology, but for hairless humans, the warmth function might have been the original driving necessity. But fire isn't portable. You can't carry it easily during daily activities. You need something wearable, something that moves with you. You need clothing. And the evidence for clothing is even harder to find than evidence for fire, because organic materials like leather and plant fibers decompose completely within centuries, leaving no fossil record. We have to use indirect evidence. The best indirect evidence comes, surprisingly, from lice. Remember earlier when we discussed the 3 types of human lice? Head lice, pubic lice, and body lice. Body lice are the key here. They live in clothing, not on bodies, because modern humans don't have enough body hair to support lice populations. When scientists sequenced the DNA of body lice and compared it to head lice, they found that body lice diverged from head lice somewhere between 83,000 and 170,000 years ago. That's when body lice evolved as a distinct species adapted to living in clothing, which means that's when humans started wearing clothing regularly enough, continuously enough, for lice to specialize in this new habitat. By around 100,000 years ago, maybe earlier, humans were wearing clothes consistently. But that's just when clothing became habitual. The first clothing use probably started much earlier, perhaps hundreds of thousands of years before. Early clothing would have been simple, probably just animal hides, draped over shoulders or tied around waists. Not sewn, not fitted, just crude protection against cold and thorns. Lice wouldn't have been able to colonize these occasional primitive garments. Only when clothing became sophisticated enough and worn continuously enough would lice find it a suitable habitat. The invention of clothing represents a cognitive leap. You have to imagine the solution before creating it. You have to understand that animal hides, which naturally belong to the animals, can be removed, cleaned, and worn. You have to develop scraping tools to clean the hides. You have to invent ways to attach skins together or fasten them on your body. Eventually, someone invented needles, creating the possibility of sewn, fitted garments. The oldest known sewing needle, made from bone, is only about 50,000 years old, but crude needles probably existed much earlier. Each innovation built on previous ones. First, draped skins, then tied skins, then fitted skins attached with sinew or plant fibers, then sewn garments made from multiple pieces, then specialized clothing for different purposes and climates. By the time modern humans were spreading out of Africa into Europe and Asia, they had sophisticated clothing systems that allowed survival in extremely cold environments. And clothing provided benefits beyond warmth. It protected skin from abrasions, thorns, insect bites. It reduced UV exposure, though this was probably less important once dark skin had evolved. It allowed humans to carry items, with pockets and wrappings enabling transport of tools, food, and materials. Clothing became a canvas for decoration and social signaling, with different garments indicating status, group membership, or personal identity. But clothing can't solve every problem. Even with fire and garments, you're still vulnerable to weather. Rain, wind, extreme heat, or cold, these require more permanent solutions. You need shelter, and shelter represents an even bigger cognitive and technological leap than clothing or fire. Other animals use shelters, of course. Birds build nests, beavers build dams and lodges, many mammals use burrows. But these are mostly instinctive behaviors, genetically programmed responses following specific patterns. Human shelter is different. It's flexible, creative, adapted to local materials and conditions. Humans build different types of shelters in different environments using whatever resources are available. The earliest shelters were probably natural features, caves and rock overhangs providing ready-made protection from weather and predators. Archaeological sites show humans using caves going back hundreds of thousands of years. But caves aren't everywhere. Many environments lack suitable natural shelters, so humans learned to build. The earliest constructed shelters were probably simple, wooden frames covered with leaves, hides, or brush. Temporary structures that could be built quickly with minimal tools. Evidence of such structures is rare because they decompose completely. But we have some tantalizing finds. Circles of stones that probably anchored wooden posts or held down hide coverings. Post holes showing where wooden supports were driven into the ground. Occasionally living floors with distinct activity areas indicating sustained habitation. The oldest clear evidence of constructed shelter dates to around 400,000 years ago. Those simpler structures probably existed earlier. By the time modern humans emerged around 300,000 years ago, shelter construction was almost certainly universal. Every human group built some form of structure for protection against weather, and shelter enabled something crucial: stable home bases. Instead of constantly moving like other primates, humans could establish semi-permanent camps, places to return to repeatedly, locations where food could be stored, tools manufactured, children raised in relative safety. Home bases allowed accumulation of possessions, development of more complex toolkits, specialization of labor within groups. Much of human social complexity might have been enabled by having stable places to live. Here's the pattern that emerges. Hairlessness created vulnerability to cold. This drove fire mastery. Fire provided warmth, but wasn't portable, driving clothing invention. Clothing and fire together still left humans vulnerable to extreme weather, driving shelter construction. Each solution enabled the next, creating a cascade of technological innovations. But these weren't just technologies. They were cognitive achievements. Fire mastery requires planning, maintaining ember stores, or knowing how to create fire on demand. Clothing requires abstract thinking, imagining how to transform materials into wearable protection. Shelter requires spatial reasoning, understanding structural principles, coordinating group effort for construction, and all of these technologies require teaching. You can't figure out fire control or clothing manufacture through trial and error in a single lifetime. These are accumulated cultural knowledge, passed from generation to generation through teaching and learning. This means hairlessness drove not just technology but also culture, language, and social learning systems sophisticated enough to transmit complex information. Think about what this means for human evolution. Other animals adapt to new environments through biological evolution, which takes thousands of generations. Humans adapt through cultural evolution, which can happen in decades or less. Move to a cold climate, and humans don't evolve thicker fur over millennia. They invent warmer clothing and better shelters within years. This cultural adaptation capability, this ability to solve problems through innovation, rather than waiting for genetic changes, this might be the most important consequence of hairlessness. By creating vulnerabilities that required technological solutions, hairlessness drove the evolution of human intelligence, creativity, and culture, and it created a feedback loop. Better technology enabled survival in harsher environments selected for individuals capable of innovation and learning. More innovative, intelligent individuals developed better technologies. Better technologies enabled expansion into even harsher environments, on, spiraling upward, until humans could survive anywhere using nothing but intelligence and accumulated cultural knowledge. The archaeological record shows this expansion. 2 million years ago, hominins were confined to Africa. 1.5 million years ago, they'd reached parts of Asia and Europe, but only warm areas. 500,000 years ago, they were pushing into temperate zones. 50,000 years ago, modern humans were colonizing Arctic regions, crossing into Australia, eventually reaching the Americas. Each expansion required better technology, better clothing, better shelter, better fire management. And here's the final piece. These technologies didn't just enable survival, they created new selective pressures. The ability to make clothing selected for manual dexterity, fine motor control, planning skills. The ability to maintain fire selected for patience, foresight, cooperation in fuel gathering. The ability to construct shelters selected for spatial reasoning, structural understanding, group coordination. Hairlessness initiated this cascade, but the cascade then shaped further evolution. The vulnerable naked ape had to become the intelligent innovative ape or go extinct. And in becoming intelligent and innovative, humans gained capabilities that transcended biology entirely. We stopped waiting for evolution to adapt us to environments. We adapted the environments to us, or created artificial environments through clothing, shelter, and fire that allowed survival anywhere. This is why hairlessness, despite seeming like a vulnerability, might have been the most important adaptation in human evolution. Not because nakedness itself was advantageous, but because the vulnerability it created drove the development of intelligence, technology, culture, and social learning systems that made humans unlike any other species on Earth. Our ancestors lost their fur and gained the world, not despite the vulnerability, but because of it. So here's the question we need to answer before we wrap this up. Why did humans lose their fur? We've explored multiple theories over the last few chapters. The savanna hypothesis, with its focus on heat dissipation and persistence hunting. The aquatic influences suggesting time spent in and around water. The parasite problem and the desperate need to reduce disease vectors. The social signaling advantages of naked, expressive skin. The technological cascade that hairlessness triggered. Which one is right? The answer is probably all of them, and none of them alone. Because here's what makes evolution so maddeningly complex and so endlessly fascinating. It doesn't usually work through single causes. Nature doesn't present organisms with one clear problem and one optimal solution. Instead, organisms face multiple simultaneous pressures, each one pushing in slightly different directions, each one creating selective advantages for different traits. And when multiple pressures happen to push in the same direction, when several different problems can all be solved by the same adaptation, evolution moves fast. Human hairlessness wasn't driven by heat stress or parasites or aquatic adaptation or social signaling. It was driven by the convergence of all these factors, each one adding to the selective advantage of losing fur, each one making hairlessness more beneficial than keeping the ancestral primate coat. Let's reconstruct what probably happened, pulling together everything we've learned into a coherent timeline. 6 to 7 million years ago, our lineage splits from the ancestors of chimpanzees and bonobos. These early hominins are fully furred, living in African forests, mostly indistinguishable from other apes except for some subtle differences in teeth and possibly early bipedalism. They have the standard primate thermoregulation system, the standard parasite loads, the standard social behaviours, nothing particularly special yet. Then the climate starts changing, Africa is drying, the Rift Valley is opening, creating new topography and altering rainfall patterns. Dense forests begin fragmenting, replaced by woodlands with more open areas. Some primate populations retreat with the forests, following their preferred habitat. These lineages will eventually become modern chimpanzees and gorillas. But one lineage, our lineage, adapts to the changing environment. They start spending more time on the ground, They begin exploiting the grasslands and woodlands that are spreading across the continent. By 4 to 5 million years ago, these hominins are committed bipeds. Walking upright on two legs has become their primary mode of locomotion. This is a huge change with cascading consequences. Bipedalism is more efficient than knuckle walking for long-distance travel. It frees the hands for carrying objects, using tools, manipulating the environment, and critically it reduces solar heat load by about 60% compared to quadrupedal posture because only the head and shoulders are exposed to direct overhead sun. But bipedalism creates problems too. Standing upright exposes more body surface to the heat, rising from sun-baked ground. Walking long distances in open environments generates substantial metabolic heat, and the savanna environment these hominins are moving into is hot. Really hot. Midday temperatures regularly exceed 100 degrees Fahrenheit. Other mammals rest during the hottest hours, but our ancestors can't afford to. They need to forage widely for food, track prey animals, search for water sources. They need to be active when other predators are resting, exploiting the temporal niche that their competitors aren't using. This creates the first pressure toward hairlessness: heat stress. A fully furred bipedal ape walking for hours under the African sun faces catastrophic overheating. The fur traps metabolic heat, prevents efficient cooling through air circulation, blocks the effectiveness of sweating. Individuals born with slightly less fur can be active longer before overheating. They can walk farther, forage more effectively, track prey more successfully. They survive better, reproduce more, pass the less hairy genes to offspring. Over thousands of generations, this pressure steadily reduces hair coverage. But that's not the only pressure. Around the same time, these hominins are changing their social structure. Group sizes are increasing. Instead of small family bands of 15 to 20 individuals, they're living in groups of 30, 40, maybe 50 or more. Larger groups provide better defense against predators and enable more sophisticated cooperative behaviors. But they also create problems. One of those problems is parasites. In small groups that move frequently, parasites have limited opportunities to build up populations. But in large groups staying in the same general area for extended periods, parasites thrive. More hosts in close contact means more transmission opportunities. Stable sleeping sites create breeding grounds for lice, fleas, and ticks. The parasite burden on individuals in large sedentary groups would have been enormous compared to small mobile groups. This creates the second pressure toward hairlessness: parasite reduction. The same reduced hair that helps with heat dissipation also dramatically reduces parasite load. Ticks can't hide in sparse hair. Lice can't establish large populations without dense hair shafts to cling to. Individuals with less fur have fewer parasites, suffer from fewer parasite-borne diseases, are healthier overall. This adds to the selective advantage of hairlessness. And it's not just parasites in general. Ticks specifically might have been a major factor. When forest-dwelling primates move into grasslands and savannas, they encounter much higher tick populations. Ticks live in tall grasses, waiting to drop onto passing animals. Our ancestors, increasingly terrestrial, increasingly moving through tick-infested vegetation, would have faced tick-borne diseases as a major mortality factor. The selective pressure to reduce ticks would have been intense. Meanwhile, these expanding hominin populations are probably also exploiting aquatic resources, not living in water like the strong aquatic ape theory claimed, but spending significant time along rivers, lakes, and coastlines, wading through shallows to collect shellfish, diving in deeper water for sea urchins or fish, using waterways as travel routes and refuges from predators. The archaeological evidence of shell middens and coastal occupation supports this. Our ancestors were comfortable around water in ways that other apes weren't. This creates the third pressure toward hairlessness: aquatic adaptation. Fur is a liability in and around water. It becomes waterlogged, loses insulating properties, creates drag when swimming, takes forever to dry, and causes skin problems from constant dampness. Hairless skin dries quickly, doesn't trap water, makes swimming and wading more comfortable. The same reduced hair that helps with heat and parasites also helps with semi-aquatic activities. So now we have three separate pressures, all pushing in the same direction: heat dissipation during terrestrial activity, parasite reduction in large social groups, hygiene and efficiency in aquatic environments. Each one alone might not be enough to drive complete hairlessness, but together they create overwhelming selective pressure. An individual born with reduced hair has advantages in multiple contexts. They cool better during persistence hunting. They have fewer parasites and diseases. They're more comfortable foraging in water. 3 separate survival advantages from one adaptation. But the benefits don't stop there. As hair coverage decreases, social communication becomes easier. Without fur obscuring facial expressions, emotional states become more visible. Blushing appears as an honest signal of social arousal. Pallor reveals fear or shock. Skin quality advertises health status. The whole body surface becomes a display of information useful for navigating complex social relationships. This creates the 4th pressure: social signaling. The same reduced hair that provides physiological advantages also provides social advantages. Better communication, more effective mate assessment, stronger social bonds through touch. Individuals who can signal and read signals more effectively have advantages in group living, in forming alliances, in choosing quality mates. Sexual selection might have favoured hairlessness once it started appearing, accelerating the process. And as hairlessness progresses, it creates new problems that require new solutions. Exposed skin burns in intense UV radiation, threatening reproductive success through folate destruction. This drives rapid evolution of dark skin pigmentation. The MC1R gene shows evidence of intense selection around 1.2 million years ago, right when major hair loss is probably occurring. Problem and solution evolving together. Similarly, hairless skin is vulnerable to cold. This drives technological innovation. Fire mastery, clothing manufacture, shelter construction. Each technology enables the next, creating a cascade. And these technologies require cognitive abilities, planning, abstract thinking, social learning. The need for technology drives brain development. Bigger brains generate more metabolic heat, requiring even better cooling, favouring even more hairlessness. It's a feedback loop, each element reinforcing the others. By around 1 million years ago, the transformation is mostly complete. Our ancestors look essentially like modern humans in terms of body hair coverage. They're hairless except for head, axillary, and pubic regions. They have dark skin for UV protection. They're using fire regularly. They're probably wearing simple clothing. They've become the naked apes. But the process isn't entirely finished. Different human populations, spreading into different environments after leaving Africa, experience different selective pressures. Populations moving into northern latitudes need to synthesize vitamin D with limited sunlight. This drives depigmentation, the evolution of lighter skin. Different populations arrive at lighter skin through different genetic routes. Europeans through one set of mutations, East Asians through different mutations. Convergent evolution, multiple solutions to the same problem. Some populations in tropical regions might experience continued selection for even more complete hairlessness in humid environments where sweating is critical. Other populations in colder climates might experience relaxed selection for hairlessness, or even slight selection for increased body hair for extra insulation. The variation in body hair coverage we see in modern human populations reflects these different recent evolutionary pressures. What we end up with is a mosaic. Human hairlessness is the product of multiple factors operating over millions of years. Heat stress drove initial hair reduction in savanna-adapted populations. Parasite loads in large social groups added selective pressure. Semi-aquatic activities provided additional advantages to hairlessness. Social signaling and sexual selection accelerated the process. Technological adaptations enabled hairlessness to work in challenging environments. UV protection through melanin co-evolved with hair loss. Cultural evolution amplified the effects of biological evolution. None of these factors alone fully explains human hairlessness. Each contributes part of the answer, and the beauty of this convergent explanation is that it accounts for the complexity of the evidence. Why do we see skeletal adaptations for running around the same time hair loss is occurring? Because heat dissipation during endurance activity was one driver. Why do we have subcutaneous fat and good breath control? Because aquatic activities played a role. Why does hair loss correlate with larger group sizes? Because parasite reduction was important. Why do we have such expressive faces? Because social signaling was part of the story. The scientific debate about human hairlessness isn't between competing theories that are mutually exclusive. It's about the relative importance of different factors that all contributed to the same outcome. Some researchers emphasize heat stress because the physiological and biomechanical evidence is strong. Others emphasize parasites because disease is such a powerful selective force. Still others highlight aquatic influences or social communication. They're all partially right. Human evolution is complex enough to accommodate multiple simultaneous selective pressures, and this convergent explanation also predicts something we can test. If multiple pressures were driving hairlessness, we should see evidence of all of them in the archaeological and genetic records. And we do. We see skeletal adaptations for sustained running and heat dissipation. We see evidence of aquatic resource exploitation. We see correlation between group size and hair loss in primate evolution broadly. We see rapid coevolution of dark skin pigmentation. We see the technological cascade of fire, clothing, and shelter appearing alongside complete hairlessness. The pieces fit together, not perfectly, because evolution is messy and the evidence is incomplete, but well enough to construct a coherent narrative. Our ancestors lost their fur because in the environments they inhabited and the lifestyles they pursued, hairlessness solved multiple problems simultaneously. Better cooling, fewer parasites, aquatic comfort, social transparency. Each advantage made hairlessness more beneficial. Together, they made hairlessness nearly inevitable. And once hairlessness appeared, it triggered consequences that shaped everything about human evolution. The need for dark skin driving pigmentation evolution, the vulnerability to cold driving technological innovation, the visible skin enabling communication driving social complexity, the requirement for clothing and shelter driving cognitive advancement. Hairlessness wasn't just one adaptation among many, it was a pivotal transformation that set humans on a unique evolutionary trajectory. We became the naked apes, and in becoming naked, we became uniquely human. Let's end where we began, standing in front of a mirror looking at yourself, your smooth skin, your naked arms, your exposed face. But now you're seeing it differently, because now you understand that this isn't just an absence of fur, this is the physical manifestation of millions of years of evolutionary pressure, technological innovation, and cognitive development. Your hairlessness isn't a minor detail of human appearance, it's the foundation of almost everything that makes you human. Think about your day today. You woke up in a shelter, probably a house or apartment, protected from weather that your naked skin couldn't tolerate. You put on clothing, artificial fur that you chose based on temperature, activity, and social context. You might have exercised, relying on your efficient sweating system to dump the heat that would have killed a fur-covered ancestor. You interacted with people, reading their facial expressions, their emotional states displayed on naked skin that can't hide what they're feeling. You made decisions based on cognitive abilities that evolved partly because your hairless ancestors needed to invent solutions to problems that fur had always solved. Every single aspect of modern human life traces back, at least partly, to the loss of our fur. Not directly, not obviously, but through chains of causation that ripple forward through evolutionary time. Hairlessness enabled persistence hunting, which provided high-quality nutrition for growing brains. Hairlessness required dark skin, which later had to lighten in northern populations, creating the diversity of human skin colors we see today. Hairlessness demanded technology, which selected for intelligence and social learning. Hairlessness enhanced communication, which enabled more complex social structures. You are a naked ape because your ancestors faced a convergence of evolutionary pressures that all pointed in the same direction. Lose the fur. And in losing it, they set off a cascade of changes that transformed a fairly ordinary African primate into something unprecedented in evolutionary history. A species that adapts to new environments not through genetic changes taking thousands of generations, but through cultural innovations happening in years or decades. A species that can live anywhere, eat almost anything, modify its surroundings rather than being shaped by them. Let's trace this cascade one more time, but now looking at the big picture, seeing how each element connects to the next. Start with climate change. Africa drying, forests fragmenting, grasslands expanding. This creates selection pressure for adaptations to open environments. Bipedalism emerges, freeing hands, reducing solar heat load, enabling efficient long-distance walking. But bipedalism in hot open environments creates thermal stress. Fur becomes a liability. Hair loss begins, driven by the advantage of better cooling during sustained daytime activity. But hair loss creates vulnerability to parasites, which are now more abundant because populations are living in larger groups in more terrestrial environments with higher tick loads. So hair loss accelerates, driven now by both cooling advantages and parasite reduction. Meanwhile, some populations are exploiting aquatic resources along shorelines and rivers. Here too, reduced hair provides advantages. Better hygiene in water, easier drying, more comfortable wading and swimming. As hair disappears, social dynamics change. Naked skin reveals emotional states, health status, individual identity. Communication becomes more visual, more nuanced, more honest. Sexual selection starts favouring individuals with clear skin advertising good health. Social bonds strengthen through enhanced tactile sensitivity. The human face becomes the most expressive in the primate world, but naked skin exposed to tropical sun faces UV damage. Folate levels drop, threatening reproductive success. Natural selection drives rapid evolution of dark skin pigmentation. Within perhaps a few 100,000 years, all humans living in Africa have very dark skin, maximum melanin production. Problem and solution evolving together, each enabling the other. Meanwhile, hairless humans are cold at night and vulnerable to thorny vegetation. This drives technological innovation, fire mastery for warmth, clothing manufacture for protection, shelter construction for weather defense. Each technology requires planning, abstract thinking, manual dexterity, social learning. The brain grows larger, not despite hairlessness, but partly because of it. Because naked apes need bigger brains to survive, and bigger brains generate more metabolic heat. A brain using 20% of the body's energy budget produces substantial heat that needs to be dissipated. This creates even more selection pressure for effective cooling systems. Hairlessness and enhanced sweating become even more advantageous. The feedback loop tightens. Better cooling enables bigger brains. Bigger brains require better cooling, selecting for more efficient cooling systems, enabling even bigger brains. By 1 million years ago, our ancestors have essentially modern human body proportions, modern human hairlessness, modern human brain sizes approaching our current range. They're using fire systematically. They're probably wearing simple clothing. They're building shelters. They're practicing sophisticated hunting strategies, including possibly persistence hunting. They have complex social structures and communication systems. They're not quite modern humans yet, but they're getting close. Then, around 300,000 years ago, anatomically modern Homo sapiens emerges in Africa. These are us, indistinguishable from people walking around today in terms of anatomy. Fully hairless bodies with retained head, axillary and pubic hair. Dark skin with high melanin content. Large brains averaging around 1,300 to 1,400 cubic centimeters. Sophisticated tool use, complex language, symbolic thought, art, culture. Everything that defines humanity, and within the next 200,000 years, these humans spread across the entire planet. Out of Africa into the Middle East, into Asia, reaching India, China, Southeast Asia, into Europe, displacing Neanderthals, into Australia by perhaps 60,000 years ago, requiring boats and showing sophisticated planning, into the Americas by at least 15,000 years ago, possibly much earlier, and everywhere they went they adapted culturally rather than biologically. Moving into cold climates, invent warmer clothing, better shelters, more efficient fires. Genetic evolution begins lightening skin for vitamin D synthesis, but cultural adaptation is faster. Moving into deserts, develop water storage, create clothing that protects from sun while allowing cooling, learn which plants provide moisture. Moving into rainforests, invent ways to preserve food in humid conditions, develop waterproof shelters, manage fungal and bacterial challenges, cultural solutions transmitted socially, spreading through populations in generations rather than millennia. This is the ultimate consequence of hairlessness. By creating vulnerabilities that required technological solutions, by driving the need for intelligence and cultural transmission, hairlessness set humans on a path towards something unique in evolutionary history. A species that transcends biological constraints through culture. A species that can inhabit any environment not by evolving specialized adaptations, but by inventing them. Look at the Arctic. Polar bears evolve thick white fur, specialized fat distribution, physiological adaptations for extreme cold. This took hundreds of thousands or millions of years of natural selection. Humans moved into the Arctic and within a few generations had invented clothing systems, portable shelters, and hunting techniques that allowed comfortable survival in the same conditions. Cultural evolution outpacing biological evolution by orders of magnitude, or consider the ocean. Whales spent millions of years evolving from terrestrial mammals to fully aquatic ones. Dramatic morphological changes, complete physiological reorganization. Humans invented boats, nets, diving techniques, and within a few thousand years were exploiting ocean resources as effectively as many marine mammals. Not through genetic changes, through cultural innovations. This capability, this liberation from biological constraint, this is hairlessness's legacy. Not the hairlessness itself, but what hairlessness required and enabled. The intelligence to solve problems technologically, the social systems to transmit solutions culturally, the creativity to invent novel adaptations rather than waiting for genetic ones, the flexibility to thrive anywhere using nothing but accumulated knowledge. And it continues today, accelerating. Modern humans create artificial environments, climate-controlled buildings where naked skin is perfectly comfortable year-round. We've essentially recreated the ancestral tropical conditions that our hairlessness originally evolved for, but we can now maintain these conditions anywhere. Arctic research stations, desert cities, high-altitude settlements, underwater habitats. Humans live in all of them comfortably because we've culturally adapted the environment to our biology, rather than waiting for our biology to adapt to the environment. We've even begun transcending our own biology in other ways. Medicine compensating for genetic vulnerabilities, technology augmenting physical capabilities, cultural institutions replacing instinctive behaviors. Some futurists speculate about further biological modifications, genetic engineering, cybernetic enhancement. But in a sense, we've been doing this since hairlessness first required us to invent clothing. We've been augmenting our inadequate biology with cultural and technological solutions for over 1 million years. Your naked skin, the smooth arm you looked at in the mirror at the beginning of this journey, it represents all of this. 1 million years of evolutionary pressure, converging selection from heat, parasites, aquatic adaptation, and social communication. Rapid coevolution of dark skin for UV protection. Technological cascades driven by vulnerability. Cognitive development fueled by necessity. Cultural transmission of accumulated knowledge. The liberation from biological constraint that made humans the dominant species on the planet. And here's the beautiful paradox. Hairlessness made us vulnerable. No protection from cold, from UV radiation, from abrasions and injuries. More vulnerable than any other primate. This vulnerability should have been our doom. Instead, it became our greatest evolutionary advantage. Because vulnerability demanded solutions, and in inventing solutions, we invented ourselves. We became tool makers because we needed tools to replace lost biological functions. We became inventors because we needed inventions to survive in environments our bodies weren't adapted for. We became teachers because we needed to transmit these inventions to the next generation. We became storytellers because we needed to preserve and share the accumulated wisdom that kept us alive. We became artists because enhanced visual communication through naked skin gave us the cognitive architecture for symbolic thought. We became builders because we needed artificial environments to replace the natural protection that fur provided. Every defining human characteristic traces back, at least partly, to the loss of our fur and the compensations that loss required. We are the species we are because our ancestors went naked into a dangerous world and survived by being clever, and then taught their children to be clever, and those children taught their children, until cleverness became our defining adaptation, more important than any physical trait, more powerful than claws or fangs or armor. So yes, you're a naked ape, bizarre among mammals, vulnerable compared to your fur-covered cousins. But you're also the descendant of survivors who turned vulnerability into advantage, who transformed weakness into strength, who lost their fur and gained the world. The next time you look in a mirror, remember, your smooth skin isn't a lack, it's a legacy. The physical evidence of the most transformative adaptation in human evolution. The adaptation that made everything else possible. The loss of our fur didn't just change what we looked like, it changed what we could become, and we're still becoming it, still inventing, still adapting, still transcending, carrying forward the legacy of those first hairless ancestors who looked down at their naked skin and decided to survive anyway. We lost our fur, and in losing it, we saved humanity.